What lies on the other side of the universe? We can look deep into space and see galaxies billions of light years away. We can measure how fast the universe is growing and even guess what it looked like just after the Big Bang. But no matter how far we look, there's always a limit, an invisible horizon that we can't see beyond. Let's explore what that really means and what might exist past it. Could the universe go on forever? Could it wrap around itself like a loop? Or are we living in a strange kind of bubble with boundaries we'll never cross? If you've ever looked up and wondered how far it all goes, this is the story you've been waiting for. Where does the universe end? And what does end even mean? When we think about space, it's easy to imagine it like a giant bubble with a clear boundary, like the edge of a balloon or the end of a map. But when scientists talk about the universe, things get more complicated. In fact, asking where the universe ends might not even be the right question. That's because the universe doesn't seem to have an edge in the way we might expect. To understand why, we have to think about how space itself works. Most of us are used to living in a world where things have boundaries. A country has a border, a field has a fence, a house has walls. But space, the very fabric of the universe, isn't built like that. It's not something sitting inside a larger space, it is space. So asking where it ends is a bit like asking what's north of the North Pole. The question doesn't quite make sense once you understand the shape of the thing you're talking about. One idea scientists use to explain this is that the universe could go on forever. This is called an infinite universe. In that case, there simply is no end. No matter how far you go, there's always more space ahead. You could travel in one direction forever and never hit a wall or a boundary. It's not that the edge is very far away, it's that there is no edge at all. This idea is hard to imagine, because in everyday life, we don't deal with infinity. But mathematically, it's possible. If space goes on and on without looping or curving back on itself, then it has no edge, it just continues. Another possibility is that the universe is shaped in such a way that if you kept going in a straight line, you'd eventually end up back where you started, like walking in a circle. This might sound strange, but it's a bit like living on the surface of a sphere, like Earth. If you start walking east and never turn, you'll eventually come all the way around the planet and return to where you began. From your point of view, it felt like you were going in a straight line the whole time. That's because Earth is curved in a way we can't always feel just by walking around. The same could be true for space itself. If the universe loops around like this, it would be what scientists call finite but unbounded. That means it's not infinite, it has a limited size, but it still has no edge. There's no border where space ends. Instead, space curves back on itself. This idea is based on Einstein's theory of general relativity, which says that space can bend and warp. If the universe has enough matter and energy, its shape could curve in on itself, just like the surface of a ball. We wouldn't see the curve easily because space is so vast, but over long distances, it might make a big difference. These two possibilities, an infinite universe or a curved, looping one, are both consistent with what scientists see when they study the cosmos. The problem is, we can only observe so much. Light travels at a certain speed, and the universe has only been around for about 13.8 billion years. That means we can only see as far as light has had time to reach us. This region is called the observable universe. It's like living inside a bubble, and we don't know what lies beyond the bubble's edge. But that edge isn't the end of the universe. It's just the limit of what we can see. Because of this, we can't be sure whether the universe is infinite or loops back on itself. Both ideas are still possible. What we do know is that there doesn't seem to be a place where everything just stops. Galaxies continue in every direction we look as far as our telescopes can see. And the farther we look, the more we see galaxies moving away from us, because the universe itself is expanding. This expansion is another reason the idea of an edge doesn't really apply. Space itself is stretching. The galaxies aren't flying through space like rockets. They're being carried apart as the fabric of space grows. Imagine dots on a balloon as it inflates. The dots get farther apart, not because they're moving, but because the surface of the balloon is getting bigger. If the universe is like that balloon, then the idea of an edge becomes even harder to picture. Where's the edge of the balloon's surface? There isn't one. You can walk along it forever without falling off. Some people might wonder, if the universe doesn't end, then what's outside it? But that question doesn't really fit either. The universe isn't sitting in something else. It's not a bubble floating in some larger space. It is all of space. If it's infinite, it includes everything. If it loops around, it's still self-contained. There's no outside to go to. Even the idea of direction gets tricky when we think about the universe as a whole. On Earth, we can point north, south, east, and west. But those directions depend on the shape of our planet. In space, those labels lose meaning. There's no universal up or down. Everything depends on your point of view. So asking where the universe ends, or what direction to go to find the edge, isn't a simple question. This all might sound confusing, but it's actually one of the most exciting parts of science. We're trying to understand something that's bigger than anything we've ever experienced. And the deeper we look, the more we realize that our everyday ideas don't apply the same way on the scale of the universe. Space doesn't behave like a room or a box. It stretches, it curves, and it may go on without end. Or it might fold in on itself in a way we haven't yet discovered. We don't know for sure, and that's part of what keeps astronomers and physicists asking questions and searching for answers. The particle horizon, our light-speed cage. When we point a telescope into space, we're not just seeing faraway places, we're also seeing back in time. Light travels at just under 300,000 kilometers per second. When we look at a galaxy that's 1 billion light-years away, we're seeing the light it gave off 1 billion years ago. We're seeing that galaxy as it was back then, not as it is today. In a way, looking out into space is like reading a history book written in light. Because of this, there's a limit to how much of the universe we can see. This distance forms what scientists call the particle horizon. It's like a giant invisible shell around us, marking the outer limit of the observable universe. But this shell isn't 13.8 billion light-years away. It's much farther than that. Space has been expanding, which means that while the light from distant objects was moving toward us, the space between us and those objects was also growing. So by the time that light reaches us, the galaxy that sent it is now much farther away than when the light first started its journey. Because of this stretching of space, the particle horizon is about 46 billion light-years away in every direction. That gives us a sphere of visible space about 93 billion light-years across. Everything inside this sphere is part of our observable universe. Everything outside it might still be part of the real universe, but we can't see it, and maybe we never will. The particle horizon isn't the limit of what exists. It's just the limit of what we can see. Inside this boundary, we can study galaxies, stars, and clouds of gas. We can map the structure of space and see how matter is spread across it. We can look back in time to the early days of the universe and even catch a glimpse of the oldest light of all, the cosmic microwave background, or CMB. This faint glow comes from a time just 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light could travel freely for the first time. That light has been moving ever since, and today we can still detect it with special instruments. But beyond the particle horizon, everything becomes invisible. There could be galaxies out there, just like the ones we see nearby. They could have stars and planets. They could have completely different structures, or maybe even life. But if they're beyond that horizon, we simply can't know. What's more, that horizon is always changing. As time passes, light from more distant parts of the universe finally reaches us. Our observable universe grows. A galaxy that was once out of reach might become visible in the future. But there's a catch. The universe is not just expanding, it's accelerating. This means that distant galaxies are being pulled away from us faster and faster. In fact, many of them are now moving away faster than the speed of light. This creates another limit called the cosmic event horizon. It marks the distance beyond which events can never affect us, no matter how much time passes. Light from anything beyond that horizon will never reach us, even in the far future, because the expansion of space will carry those objects away faster than light can catch up. It's a kind of one-way barrier. Once something crosses that distance, it's gone forever, not just hidden from view, but permanently out of touch. So while the particle horizon tells us how far we can see right now, the cosmic event horizon tells us how far we can ever hope to see, even with unlimited time. Both horizons shape our understanding of the universe. They remind us that what we observe is just a piece of a much larger reality, and that reality could be far bigger than we can imagine. It's also humbling. We want to understand the universe as a whole, not just the part we can see, but the total picture. We want to know how big it is, what shape it has, and whether it had a beginning or will have an end. But the speed of light and the age of the universe set hard boundaries on what we can observe. No telescope can reach beyond that limit. No spacecraft can go that far. That doesn't mean science stops there. Astronomers use what they can see to make careful guesses about what lies beyond. If the universe looks the same in every direction, and if the laws of physics don't change from one place to another, then maybe the rest of the universe is much like what we see inside the particle horizon. That's one of the basic ideas behind cosmology, that the universe is uniform on large scales. But it's still an assumption, not something we can test directly. We may never know how big the universe truly is, but within our light speed cage, we can still explore, still discover, still learn. Every new observation adds to our map of the cosmos, even if the map will perhaps always be incomplete. Why the universe keeps slipping away? We often hear that nothing can go faster than light. That's true, but only when we're talking about objects moving through space. The expansion of the universe is different. It's not about motion through space. It's about space itself stretching. That stretch has no speed limit. The farther away a galaxy is from us, the faster it appears to be moving away. That relationship is described by something called Hubble's law, named after the astronomer Edwin Hubble. It says that the speed at which a galaxy recedes from us is proportional to its distance. Double the distance, and you double the speed. And there's a point where this speed crosses the speed of light. That distance is called the Hubble radius. So what does that mean in practice? It means that even though those galaxies exist, their light will never reach us. They are beyond the reach of any signal or any future communication. It's like trying to run up an escalator that's moving down faster than you can climb. We live in a time when we can still see galaxies that are far away, but there's a kind of ticking clock. Some of the light we're receiving now left those galaxies billions of years ago. Today, those same galaxies are much farther out, and many of them are already beyond the Hubble radius. If they were to send us new light right now, we would never receive it. We are already losing touch with them, even though their ancient light is still arriving. This effect is tied to the acceleration of expansion. Scientists discovered this in the late 1990s, when they were studying distant supernovae, exploding stars used to measure cosmic distances. What they found was shocking. Instead of slowing down, the expansion of the universe was speeding up. Some unknown force, now called dark energy, is pushing space apart faster and faster. That means even more regions of the universe are being pulled beyond our reach. Scientists believe that if the universe continues to expand at this rate, or even faster, then someday most of the galaxies we see today will disappear from view. It will happen gradually. Their light will grow fainter, stretched into longer wavelengths, until it fades entirely. In the very distant future, only the galaxies that are part of our local group, our cosmic neighborhood, will remain visible. Everything else will have slipped away forever. Observations from the Hubble Space Telescope and from satellites like WMAP and Planck all point to the same picture. The universe is not just getting bigger, it's racing away from itself, and we are inside it, watching the sky slowly empty. When we see a galaxy 10 billion light-years away, we're seeing it as it was 10 billion years ago. But because of expansion, that galaxy is now much farther than 10 billion light-years. It might be over 30 billion light-years away today. And if we calculate how long it would take for light to reach us from that galaxy now, the answer might be never. We caught a glimpse of its past, but we'll never see its present. The Hubble radius changes over time as the universe changes. Some galaxies might still be inside the boundary today, but just barely. In a few billion years, they'll cross over. Their light will no longer be able to make the journey. Their stories will end, at least for us. And yet, even though we know this is happening, we continue to study the sky. We map the fading light. We build better telescopes. We gather ancient photons from the edge of what's visible, because each one of them carries a message, from galaxies now lost, from regions we'll never visit, from a past we can barely imagine. The universe is not shrinking, but it is slipping away. The last visible light, tracking the farthest photons. If you look up at the night sky, the stars you see with your eyes are all part of our own galaxy. They're not that far away compared to the rest of the universe. Some are a few dozen light-years distant, others are a few hundred. That might sound like a lot, but in cosmic terms, it's nothing. The real story begins far beyond what we can see with the naked eye. With telescopes, we can look much farther. We can collect light from galaxies so far away that their glow has traveled across space for billions of years just to reach us. That light has been moving since long before the sun was born. It's some of the oldest light we can detect from stars and galaxies, the last visible light from the far reaches of the observable universe. Every time we spot one of these distant galaxies, we're looking into the deep past, all the way back to a time when the universe was young. Some of these galaxies formed only a few 100 million years after the Big Bang. Their light has been traveling ever since, stretched by the expansion of the universe as it made its way to us. By the time it gets here, it's no longer visible to human eyes. The light waves have been stretched into longer, redder wavelengths. That's why astronomers call it redshifted light. Redshift tells us how far away a galaxy is and how long its light has been traveling. The higher the redshift number, the farther the object and the older the light. For decades, scientists pushed to find galaxies at higher and higher redshifts, getting closer to the beginning of time. Then came the James Webb Space Telescope. Launched in late 2021, it was built to see infrared light, the kind of light that old galaxies give off after their visible light has been stretched by cosmic expansion. Webb's mission was to find the very first galaxies, the earliest points of light in the universe's history. In just its first year, Webb spotted several candidate galaxies with redshifts above 10. That means their light had been traveling for over 13 billion years. Some of them may have formed just 300 million years after the Big Bang. They are faint, small, and unlike most galaxies we see today. But their light is real. And it tells us something powerful, that stars and galaxies were already forming when the universe was still in its infancy. These galaxies are more than just distant smudges on a map. They carry clues about what the universe was like long ago. Back then, everything was hotter and denser. Galaxies hadn't settled into their familiar shapes yet. There were no spiral arms, no big clusters, no heavy elements like iron or gold. The first stars were huge, fast-burning and short-lived. When they exploded, they helped seed the cosmos with the elements needed for later stars, for planets, and eventually for life. By studying the light from these ancient galaxies, astronomers are learning how the early universe changed over time. They look at the colors in the light to find out what kinds of stars were there. They measure the brightness to estimate how much gas and dust filled those galaxies. They use the shape and spread of the galaxies to figure out how gravity was pulling things together. Some of the galaxies found by Webb seem brighter and more active than expected. How did they form so quickly? Why are they so developed at such an early time? These are mysteries still being studied. But the light we see, those final stretched out photons from long ago, gives us a direct link to that ancient era. There is a limit, though. No matter how powerful a telescope becomes, we can't see back to the very beginning. Before galaxies and stars, the universe was filled with a glowing fog, a hot plasma of particles and light. Light couldn't travel freely in that early soup. It kept bouncing off particles like a flashlight beam in thick mist. That fog only cleared about 380,000 years after the Big Bang. That's when the universe cooled enough for atoms to form, and light could finally stream across space. That glow, the CMB, is not the same as starlight, but it's the oldest light of any kind that we can detect. It fills the universe like a soft hum in every direction. Special satellites like COBE, WMAP, and Planck have mapped this background in great detail. They show tiny variations, little hot and cold spots that match the seeds of future galaxies. These were the first signs of structure in the universe. But the first visible light from stars came later. That's what Webb is trying to find. The first galaxies. The first starlight that ever escaped into the darkness. And that's what we call the last visible light. The faintest, oldest light we can still track from the edge of the observable universe. Photons from those first stars are rare. Most of them have been scattered, absorbed, or lost to time. The ones that survive are precious. Each one carries a bit of history. They move across space for billions of years, avoiding dust clouds, slipping past galaxies, dodging all the dangers of a changing cosmos. Then, at just the right moment, they strike the mirror of a telescope or a satellite detector and reveal their journey. When scientists collect this light, they see a story of how stars were born, how matter came together, how light broke free from the darkness, and they see something else too, a reminder that we are part of that same story. The atoms in our bodies were made in stars like the ones we study. The same photons that shaped the early universe now shape our understanding of it. What the CMB isn't telling us about what lies beyond. The CMB is our best view of the early universe. It's smooth but not perfectly smooth. Tiny temperature differences show up as patterns, like faint spots and ripples. These patterns are small, but they carry a lot of meaning. They show where matter was just a little bit denser or cooler than average. And those small differences eventually led to the galaxies, stars, and clusters we see today. The CMB has helped scientists figure out the shape of the universe, its age, and even how fast it's expanding. But while it's the oldest light we can see, it's also a kind of cosmic wall. We can't see past it, not with light anyway. The CMB marks the limit of what we can detect with light, and this is where the mystery begins. The CMB tells us a lot about what was happening up to that point, but it tells us almost nothing about what might be beyond it. We know what the early universe looked like inside our observable bubble. But what lies outside that bubble is hidden. It could be more of the same, or it could be something very different. We just don't know. The patterns in the CMB don't reveal what's beyond our cosmic horizon. They show us how matter was distributed in the early universe, where we are, but not what happened in other regions that are too far away for their light to reach us. That's a key limitation. The CMB acts like a shell around us, but it's not a complete map. It's more like a local snapshot from a certain time, frozen in all directions. Some scientists have wondered if the CMB might contain hidden messages, signs of strange things just outside our view. What if other parts of the universe had slightly different laws of physics? What if there were massive structures like other universes bumping into ours? In theory, those could leave marks in the CMB, but so far, no clear signs have been found. What we do see is a fairly smooth and even background with tiny bumps here and there. Those bumps are random as far as we can tell. There are no obvious patterns that suggest something strange lurking just out of reach. That might mean the universe is pretty uniform beyond the CMB, or it might mean we just don't have the tools to notice the difference. The CMB only shows us information carried by light. But light isn't the only thing in the universe. Other signals, like gravitational waves or neutrinos, might carry messages from earlier times or from places beyond the CMB's edge. But those signals are incredibly faint and hard to detect. Our technology is just beginning to reach the sensitivity needed to try. Gravitational waves, for example, are ripples in space itself. They were predicted by Einstein and finally detected in 2015. These waves can pass through matter and don't get scattered the way light does. In theory, some gravitational waves from the earliest moments of the universe could still be passing through us. If we could catch them, they might tell us what was going on before the CMB formed. But detecting those early waves is a huge challenge. The ones we've seen so far come from black hole and neutron star collisions, not from the early universe. There's also the problem of the universe's own noise. The CMB is not a perfect image. It's filled with tiny distortions caused by the matter the light passed through on its way to us. Galaxies, clusters, and clouds of gas have all affected that ancient glow. The signal has been tugged and twisted. Scientists work hard to clean it up, to subtract the local effects and reveal the original light. But even the best data has limits. At some point, we just can't be sure what the signal means or what it might be hiding. And so we're left with a strange situation. We can see the oldest light, but we can't see the oldest events. We can measure the CMB in incredible detail, but it doesn't show us what's outside our cosmic bubble. It can't tell us if the universe is infinite, or if there's a boundary, or if something entirely unexpected is out there. It also can't tell us if other regions of space had different beginnings. Some theories suggest that the Big Bang wasn't the only one. There could be many bubbles of universe, each with its own version of physics, scattered like foam in a larger multiverse. If that's true, the CMB might be showing us just one small piece of a much bigger picture. But again, there's no way to test that directly, at least not yet. The CMB gives clues that the universe is flat on large scales, meaning parallel lines stay the same distance apart. But we don't know if that flatness goes on forever. Space could curve subtly beyond our view. It might loop back on itself or bend in strange ways. The CMB shows us one slice of time, one layer of the universe, and it stops there. Beyond it is a silence we can't cross, not with light, not with radio, not with anything we currently know how to use. So we keep looking for other signs. We study galaxies, quasars, dark matter, and the way space itself expands. We measure background signals, gravitational lenses, and temperature shifts in ancient gas clouds. We build better detectors, launch new missions, and wait for new data. Every step gets us closer. But the edge remains, the place where light ends and the unknown begins. Cosmic inflation, when the universe outsprinted itself. In the first moments after the Big Bang, something strange happened. Something that still leaves scientists puzzled today. The universe didn't just expand. It exploded outward at a pace that defied everything we normally understand about speed and motion. This idea is called cosmic inflation. It was an event so fast and so extreme that space itself seemed to stretch faster than the speed of light. In a tiny fraction of a second, space may have grown from something smaller than an atom to something larger than a galaxy, and it kept going. The reason scientists believe this happened has to do with how smooth and even the universe looks today. When we look at the CMB, we see that it's surprisingly uniform. No matter which direction we look, the temperature is nearly the same. That's strange because without inflation, those different parts of the sky should never have been able to interact or even know about each other. They should have been too far apart, with no time for light or energy to travel between them. Inflation solves this by saying that everything we see today was once packed into a much smaller space, a space where light and heat could easily spread out and make things even. Then, suddenly, that space grew at an incredible speed, locking in those smooth conditions and carrying them across vast distances. This wild burst of expansion probably lasted less than a trillionth of a second, but its effects were huge and long-lasting. It stretched the very shape of the universe and left behind tiny wrinkles, fluctuations that later grew into galaxies, stars, and everything else we see today. Without inflation, the universe might look completely different. It might be clumpier or more chaotic. It might not have formed galaxies the way it did. In some ways, we owe the structure of the cosmos to that tiny moment. But inflation also created a strange side effect. It pushed parts of the universe so far away from us that we'll never be able to reach them, or even see them. No matter how long we wait, their light will never catch up to us. Inflation didn't just shape what we can see, it also hid much of the universe from view. Some scientists think inflation could still be happening in other parts of the universe, far beyond our reach. In this idea, called eternal inflation, new pockets of space keep inflating and forming new regions, possibly with different laws of physics. Each of these could be a kind of universe in itself, like a bubble in a never-ending foam. We live in one bubble, but there could be countless others, all created by inflation that never really ended. If that's true, then the universe we know is just a small part of something far larger and more complex. The horizon we see isn't the edge of everything, it's just the edge of our visible patch. Beyond it could be more galaxies, more stars, and maybe even completely different forms of matter or energy. And we'll never know for sure, because inflation has locked those regions behind a barrier of distance and time. One of the biggest goals in modern astronomy is to find direct evidence of gravitational waves from inflation. They're incredibly faint, but they could hold the key to proving that inflation really happened. Special experiments like BICEP are searching for these ripples. It's a tough challenge. The signals are buried in noise and may be mixed with other sources of radiation. But if we ever detect them, it would be a major step in understanding the moment when the universe outsprinted itself. The idea of inflation forces us to think differently about space, time, and causality. It means that some parts of the universe will always be cut off from us. And yet, we feel their presence in subtle ways. The smoothness of the sky, the structure of galaxies, the tiny bumps in the microwave background. All of these are echoes of inflation. They're the footprints of a time when physics was pushed to its limits, and the universe was being reshaped at a scale we can hardly imagine. Even though inflation happened in the blink of an eye, it changed everything. It created a horizon beyond which we cannot see, and possibly never will. It may have spawned other worlds, other versions of reality, still expanding beyond our reach. The inflationary multiverse. Is our universe just one patch in an infinite quilt? The inflationary multiverse is a picture of reality that looks more like a quilt, or maybe a giant foam made of endless bubbles. Our universe would just be one small patch, one bubble floating in a much larger space that never stopped growing. Each of these bubbles could have different properties. In our universe, the laws of physics allow atoms to form, stars to shine, and life to appear. But in another bubble, the rules could be totally different. Gravity might be stronger or weaker. Light might not behave the same way. Atoms might not be stable. Entirely different forms of matter could exist, or maybe no matter at all. In some regions, the conditions might be too wild, too unstable for anything like stars or galaxies to take shape. In others, something completely unfamiliar could evolve, structures we couldn't even imagine. The theory of inflation was built to solve problems like the even temperature of the universe or the smoothness of space. But once you start looking closely at how inflation works, the idea of a multiverse seems to naturally follow. It falls out of the equations almost like a side effect. If inflation starts, it's hard to make it stop everywhere. Some areas cool down and become universes like ours. Others keep going. The process never ends. The space in which all this happens is often called the inflating background, or sometimes the false vacuum. It's a place where energy is high and unstable. As patches of this space decay and cool, they turn into individual universes, each one bubbling out of the inflationary sea. Once a universe forms, it stops inflating inside, but the surrounding space keeps expanding. That's why the bubbles stay apart. They can't collide, They're moving away from each other faster than anything can travel. In this picture, our visible universe is just a small part of one bubble. The rest of the bubble, the parts beyond our cosmic horizon, might be full of galaxies we'll never see. And beyond that, other bubbles continue to form, forever cut off from our view. They may as well be in a different reality. One of the strange consequences of this model is that it changes how we think about fine-tuning. Many scientists have noticed that the laws of nature seem finely tuned for life. If things like the strength of gravity or the charge of an electron were just a little different, stars might not form or chemistry might not work. In the inflationary multiverse, this fine-tuning might not be surprising. If countless universes exist, each with different settings, then it's not strange that at least one of them has the right conditions for life. We just happen to live in that one, because we couldn't be anywhere else. Each bubble becomes a kind of cosmic experiment, each one with its own rules, its own history, and its own fate. Some might burn out quickly, others might last for trillions of years. Some might be full of stars and galaxies. Others might never form a single atom. But if we can never observe these other bubbles, how can we know they're real? Science usually depends on observation and evidence. We build theories, make predictions, and then test them. But the multiverse, by its very nature, lies beyond observation. The other universes are out of reach. We can't send probes to them. We might never see them, even indirectly. Some researchers have tried to find signs that other bubbles might have touched ours in the distant past. Maybe, just maybe, our universe had a close encounter with another bubble early in its life. If that happened, it could leave a mark, perhaps a weird pattern in the distribution of galaxies. But so far, no clear evidence has turned up. The sky looks smooth and undisturbed as far as we can tell. Still, some scientists argue that the multiverse idea shouldn't be dismissed just because it's hard to test. After all, it comes from a theory, cosmic inflation, that does explain things we can see. If inflation is right, and if eternal inflation naturally follows from it, then maybe the multiverse is a real consequence we have to take seriously, even if we can't visit those other universes. The math behind this picture is complicated, but the basic idea is surprisingly simple. Start with a region of space filled with energy. Let that space inflate rapidly. Occasionally, little patches cool down, stop inflating, and form universes. The rest keeps growing. More patches form. Each one becomes a separate universe, sealed off from the others by space that stretches faster than light. The process goes on forever. This endless production of universes raises many questions. Are there infinite versions of reality? Could some of those universes be nearly identical to ours? Could there be other Earths, other people, even other versions of ourselves? It's hard to say. If the number of universes is truly infinite and the possibilities are vast, then some regions might end up repeating by pure chance. But that's a tricky idea, and not everyone agrees on what it would mean. Whether or not we ever find direct evidence of the multiverse, the idea forces us to think bigger than ever before. Not just about how big the universe is, but about how many different kinds of universes might exist. And it all starts with that tiny moment, just after the Big Bang. From that moment forward, the universe was never just one thing. In some ways, this brings us full circle to ancient questions. For thousands of years, people have wondered if the universe is infinite. Now, science is telling us that it might be, not just in space, but in form. Not just one infinite universe, but an infinite number of universes, each one unfolding with its own set of rules, a cosmic archipelago with each island forever drifting apart. Cosmic distance ladder, measuring the unseeable step by step. Measuring the universe is not like measuring things on Earth. There are no ropes we can stretch across galaxies, no rulers that go beyond the moon, but somehow, astronomers have figured out a way to measure those great distances anyway. They do it step by step, using what's known as the cosmic distance ladder. It's called a ladder because each method depends on the one before it. You start with the closest things, where simple geometry works. Then you move to slightly farther things, using what you've learned to measure the next level. Bit by bit, the ladder climbs outward, eventually reaching galaxies billions of light years away. Each step builds on trust and careful checking. If the bottom of the ladder is off, then the top is off too. That's why accuracy matters from the very start. The first rung on the ladder is something called parallax. It's the most direct way to measure distance to nearby stars. The idea is simple. As Earth moves around the Sun, a nearby star appears to shift slightly in the sky compared to the background stars. This tiny shift, measured in fractions of a degree, can be used to work out how far the star is. The trick is in how small the movement is. Even the closest stars only move a little. For a star just a few light years away, the angle might be less than 1 arcsecond, like seeing a coin move from across the length of a football field. Satellites like Hipparcos and Gaia have been used to measure these tiny angles with great precision. Thanks to them, we now know the distances to thousands of nearby stars with great confidence. This is the solid base of the ladder. Everything else relies on these measurements being right. Once we know the distances to nearby stars, we look at the way they shine. Some types of stars have a very steady pattern. They pulse or vary in brightness in a predictable way. These are called variable stars, like Cepheid variables. The time they take to brighten and dim tells us something about how bright they really are. And once we know their true brightness, we can compare that to how bright they look from Earth. The difference tells us how far away they must be. This method lets us reach farther out, to stars in other galaxies. Cepheid variables are bright enough to be seen in nearby galaxies like Andromeda. So now we can measure the distance to those galaxies by using stars inside them. Stars we understand thanks to the ladder's lower rungs. But the ladder doesn't stop there. Next come Type Ia supernovae. These are exploding stars that reach a specific brightness every time. It's like having a cosmic light bulb with a known wattage. When we spot one of these supernovae in a distant galaxy, we can again compare how bright it should be to how bright it looks. That tells us how far away the galaxy is. This step takes us far into the universe, billions of light years away. It's one of the most powerful tools we have. These supernovae also helped reveal that the universe's expansion is speeding up. Without them, we might never have discovered dark energy. But measuring even farther distances and understanding the full scale of the universe means using redshift. It's a little like the Doppler effect you hear when a train passes. The sound stretches out and lowers in pitch. For light, the stretch means longer wavelengths, and longer wavelengths mean redder light. In the early 20th century, astronomers like Edwin Hubble noticed that distant galaxies all showed redshift. The farther away they were, the greater the redshift. This meant the universe was expanding, and that space itself was stretching the light as it traveled. That discovery gave astronomers a new tool. Now, by measuring how redshifted a galaxy's light is, we can estimate how far away it is, at least on a large scale. But redshift only works well if we understand how the universe expands. The speed of expansion is known as the Hubble constant. If we get the Hubble constant wrong, then our distance guesses will be off. That's why astronomers try to measure the Hubble constant in many different ways, using Cepheid stars, supernovae, the CMB, and more. Each method gives a slightly different answer, and this has led to what's called the Hubble tension. It's one of the biggest puzzles in astronomy today. Still, redshift remains our best tool for mapping the farthest reaches of the universe. It's used to estimate the distance to galaxies we'll never visit and whose stars we can't separate. When astronomers talk about seeing a galaxy 13.2 billion light-years away, that number often comes from redshift measurements. We're looking at light that's been stretched as space expanded, trying to match it with our models of how fast the universe has grown. But redshift isn't perfect. At very high distances, the light becomes so red that it's almost invisible to traditional telescopes. That's why telescopes like James Webb are so important. They can see in infrared. Without that capability, the upper rungs of the distance ladder would stay in the dark. The ladder, as it rises, also depends on calibration. That means going back to the lower rungs and making sure everything still checks out. Gaia's better measurements of parallax, for example, have helped improve our understanding of Cepheids. Better supernova data has helped refine redshift models. It's a constant feedback loop. The more we learn at one level, the better we understand the ones above and below. There's another layer too, galaxy clustering and standard rulers. This uses large-scale patterns in the way galaxies are distributed across space. Some patterns, like the baryon acoustic oscillations, serve as yardsticks for the universe. They formed from ripples in the early universe, and those ripples left behind a kind of regular spacing between galaxy clusters. By measuring that spacing at different distances, astronomers can track how the universe has expanded over time. It's yet another way to climb the ladder, even higher, even farther. Each rung is fragile on its own, but together they form a kind of web. It's not perfect, but it's strong enough to support our biggest questions. How big is the universe? How old? How far can we see? How fast is it changing? None of these answers come from a single measurement. They come from layers of work, each one leaning on the last. When expansion breaks our rulers, suppose you want to ask how far away a distant galaxy is. The answer depends on how you ask the question. Do you want to know how far the light has traveled? Do you want to know how far away the galaxy was when it sent that light? Or do you want to know how far away it is now, while the universe has been expanding the whole time the light was moving? All three are valid, but they give very different numbers. Astronomers have different terms for these different kinds of distance. One is called comoving distance. This is like saying, let's freeze the expansion of space right now. If we took a giant ruler and stretched it across the universe, how long would it be from here to that galaxy? This number stays the same over time, even as the universe expands. It gives a stable frame of reference to compare different distances. Another kind of distance is called light travel distance. That's how far the light has moved through space. It matches the age of the light in years. So if we see light that's 13 billion years old, we know the light has been traveling for 13 billion light years of time. Then there's angular diameter distance, which is more visual. Imagine you're looking at a faraway object, like a galaxy, and trying to work out how big it is by how much space it takes up in the sky. This kind of distance is about how big the object looks, not how far it's actually sitting in today's universe. Strangely, because of the way space expansion and redshift work together, galaxies at a certain range of distance can actually appear bigger the farther away they are. This goes against our everyday sense of how perspective works. Each of these distances tells a different part of the story. And because the expansion of space changes over time, each kind of distance is tied to when you're measuring it. Early in the universe's life, the expansion was slower, then it sped up. This means that galaxies farther away live in a very different expansion environment than the one we live in now. In many ways, measuring space is like trying to measure something while the tape measure is made of rubber and constantly being pulled in every direction. To deal with all this, astronomers rely on models. These models use math to describe how space has expanded over time. They use real observations, like the redshifts of galaxies, the brightness of supernova, and the temperature of the CMB, to test how accurate those models are. Then they use the models to make sense of what distance even means in this strange, shifting universe. But even with the best models, our measurements are only as good as the assumptions we put into them. If the expansion rate is different in some parts of the universe, or if dark energy changes over time, then our rulers will give the wrong answers. And there are still mysteries in those areas. We don't know what dark energy really is. We don't know why the expansion seems to be speeding up. We're using a ruler to measure something that's not only growing, it might be changing its growth rate as it goes. So the challenge isn't just about measuring faraway things. It's about measuring in a world where the ground beneath your feet is stretching. The cosmic distance ladder gave us a way to climb, but expansion keeps twisting the ladder as we go. Topology of the cosmos. Could the universe loop back on itself? Space doesn't always follow the rules of everyday objects. It can twist and bend in ways that don't match up with how we picture things in our daily lives. One of the most fascinating ideas in modern cosmology is that the universe might not be infinite, but also might not have an edge. In some games, when you move your character off the right edge of the screen, they reappear on the left. Move off the top and you come back from the bottom. It's as if the game world loops around, forming a kind of connected surface. The player never sees an edge. No matter which way they go, they're always inside the game world. Now imagine that, but in 3 dimensions, with space instead of pixels, and you begin to get a sense of what cosmologists mean by a looping universe. In math and physics, this idea falls under a field called topology. You can stretch, twist, and deform shapes in topology as long as you don't tear them or glue them. A classic example is a donut. A donut and a coffee mug are topologically the same because you can reshape one into the other without cutting or breaking it. The hole in the middle matters more than the shape of the surface. So if we think of the universe topologically, the big question is, does it have a hole? Does it loop? Or does it just go on forever? One model suggests the universe might be like the surface of a sphere, but in 3 dimensions, not 2. A sphere's surface is finite. It has a limited area, but it has no edges. If our universe works the same way in higher dimensions, then it could be finite in volume, but have no outer wall. But that's not the only option. There are more exotic possibilities. The universe could be like a 3-dimensional torus, a fancy word for a 3D donut. Or it could have a more complex shape, something twisted or folded in ways that are hard to picture. These shapes would still allow space to loop back on itself, and we wouldn't be able to see a wall, even with the best telescope. Every direction would still look infinite, but it wouldn't be. Scientists have tried to look for signs that space might repeat. One idea is to search for matching patterns in the CMB. If the universe loops, then that light might have traveled all the way around the cosmos and come back to us from more than one direction. Like echoes bouncing off the walls of a room, we might see the same spots in the sky appearing more than once. So far, no repeating patterns have been found with confidence. But the data is hard to read, and the sky is noisy with all kinds of signals. It's still possible that the universe loops on scales larger than we can see. Even if space doesn't loop, it could still be shaped by forces we can't detect directly. Space might be curved, just like a piece of paper can be bent into a cylinder or rolled into a cone. In general relativity, mass and energy curve space. Light follows that curvature. Galaxies move through it. Depending on the overall shape of space, the whole universe could curve back on itself or stretch out endlessly. If the total amount of energy in the universe is just right, space will be flat. But if there's a bit more or less, it might curve like a saddle or a sphere. Measurements of the CMB suggest that our universe is very close to flat. But very close doesn't mean exactly flat. It just means that if space curves, it does so very gently, so gently that even across billions of light years, we haven't seen it. That leaves the door open for a looping universe. The horizon of the visible universe could be just a tiny patch on a much larger surface. Some physicists have also wondered if looping space might leave behind other clues. For example, if light from distant objects traveled around the universe and arrived at Earth more than once, we might see ghost images, faint doubles of galaxies in different parts of the sky. These doubles would look like copies, but be from the same original object, seen at different times. Detecting this would be extremely difficult. The light would have traveled a long, twisted path, and the object might have changed or faded since then. But it's another way scientists are testing the shape of the universe. The idea of a looping universe also raises strange possibilities about movement and time. If you flew a spaceship fast enough and waited long enough, could you see the back of your own head? Could you return to Earth from the opposite direction, having looped around the cosmos? In theory, yes, if space is small enough and loops in the right way. But in practice, The universe is so large and expanding so quickly that any such trip would take far longer than the age of the universe itself. The path would grow as you traveled. You might never catch up. Still, thinking about the topology of space helps us step outside our everyday sense of direction. It reminds us that the universe may be playing by rules we aren't used to. Just because we can't see a wall doesn't mean space goes on forever. The universe may simply have twists and turns too large or too subtle for us to detect. Is it a boundless ocean, a closed sphere, a folded, twisting, self-connecting maze? These are not just different shapes. They're different answers to the question of how space works, how big everything is, and whether infinity is real or just an illusion. Flat, closed, or open to the infinite. If the universe is flat, then space works the way we learned in school. A triangle's angles add up to 180 degrees. Parallel lines never meet. Light travels in straight lines that go on forever. This is the kind of space we're most familiar with. It's the geometry of a sheet of paper stretched out endlessly. In a flat universe, if you shine a flashlight into space, its beam keeps going straight, forever, unless something gets in the way. Now imagine a different kind of space, one that's curved inward like the surface of a ball. This is called a closed universe. On a small scale, it might seem flat, but over huge distances, space bends. Triangles add up to more than 180 degrees. Lines that start out parallel might slowly come together and meet. If you travel in a straight line for long enough, you might return to where you started, even though you never turned. Then there's the third option, an open universe. This kind of space curves outward like a saddle or a trumpet. Here, triangles add up to less than 180 degrees. Lines that start off in the same direction drift apart forever. Space stretches out endlessly, not just in size, but in the way it bends. This universe is infinite, like the flat one, but in a very different way. It expands in all directions and never comes back around. Each of these shapes come from general relativity. That theory says the shape of space depends on how much energy and matter the universe contains. In a universe with just the right amount of stuff, just the right balance between mass, energy, and the force of expansion, space comes out flat. If there's more matter than that critical amount, space curves inward and becomes closed. If there's less, space curves outward and becomes open. So, how do we figure out which one we live in? Over the last few decades, measurements from satellites have looked closely at the CMB. Their results suggest that the universe is very, very close to flat. The angles match up with the predictions of flat space, but there's still some wiggle room. The measurements aren't perfect, and there's always a small chance that space could curve slightly, either inward or outward, just beyond what we can detect. A flat universe is special. It means the universe has just the right amount of energy to balance gravity and expansion. It's like standing a pencil on its tip. Not impossible, but it seems unlikely unless something put it there. That's one reason scientists think inflation played a role. That sudden stretching would have smoothed out any curves, making the universe look flat even if it started out lumpy or bent. Inflation, if it happened, would explain why the universe looks so balanced today. But even if the universe is flat, that doesn't mean it's simple. Flat space can still loop back on itself. A flat sheet can be folded into a cylinder or a torus. Flat doesn't always mean infinite, and infinite doesn't always mean flat. The shape and the size are related, but they're not the same. If the universe turns out to be closed, then it's truly finite. It has a limited volume. There's only so much space, only so many galaxies, and only so far you can travel. That idea feels comforting to some people. It suggests a contained world, with boundaries we can map, even if we can't ever reach them. But a closed universe also comes with a warning. Gravity might eventually win the battle against expansion. The universe could slow down, stop growing, and begin to shrink. In the far future, it might collapse back in on itself in a big crunch. An open universe tells a very different story. In that model, space keeps stretching forever. Galaxies keep moving apart. Over time, the universe gets colder, emptier, and darker. Stars burn out, black holes fade, even atoms might come apart in the end. This heat death takes trillions upon trillions of years. But it's a quiet ending, just an endless spread into darkness. Each model of the universe's shape carries its own vision of what lies beyond, and all of them, in their own way, challenge our sense of what it means for something to be infinite, or complete, or real. Can infinity exist in reality, or only in math? Infinity is a strange idea. It doesn't work like regular numbers. You can't hold it in your hand. You can't reach it by counting. But in math, infinity makes sense. It shows up in equations, in geometry, and in theories that describe space, time, and energy. In math, you can draw a line that never ends. You can imagine numbers that keep going without stopping. But when it comes to the real world, when we ask if infinity can actually exist in nature, it becomes much harder to answer. The question touches both science and philosophy. In math, infinity is treated like a useful tool. But in physics, everything depends on what we can measure. If the universe is infinite, then it has no limit to its size. It might have an infinite number of stars, planets, and galaxies. It's something with no end at all. The first place we meet infinity in the universe is space itself. When we look at the night sky, we see thousands of stars. With telescopes, we see billions of galaxies. Each one holds billions of stars, and those galaxies continue in all directions. The farther we look, the more we see. So the question becomes, does this go on forever? Or is there a point where it stops? If the universe is infinite, then it raises strange consequences. An infinite number of stars, an infinite number of planets. That would also mean there might be other versions of us, copies living on planets just like Earth, somewhere so far away that their light hasn't reached us and never will. These are the kinds of thoughts infinity invites. Now, think about time. Can time be infinite too? We often imagine time stretching from the past into the future. The Big Bang gives us a beginning, at least in our current understanding. But will time have an end? Or will the universe keep going forever? If the universe keeps expanding, especially if dark energy continues to push galaxies apart, then time might go on without end. The universe would get colder, emptier, and quieter, but it wouldn't stop. Time would keep flowing. That's an infinite future. But again, we can't observe that far ahead. We can only build theories based on what we see now. In physics, infinity often shows up as a warning sign. When a theory produces an infinite result, like infinite energy or density, it usually means something is wrong. For example, the center of a black hole is called a singularity. That's where, according to general relativity, the density becomes infinite. But most scientists think this just shows that the theory breaks down in extreme conditions. A better theory, maybe one that includes quantum gravity, might fix the problem. The same thing happens at the start of the universe. If the Big Bang began from a point of infinite density, that again suggests we're missing something. Infinity, in these cases, isn't treated as a real thing. It's treated as a clue that we need a deeper explanation. Still, some infinities in physics are taken seriously. The idea that space might be infinite in size is not rejected outright. It's treated as a possibility. A very strange one, yes, but one that fits some models and data. If space really is infinite, then we live in a reality with no boundaries. Our brains are built to think in terms of objects and limits. We like beginnings and endings, but the universe might not follow those rules. Philosophers have thought about infinity for thousands of years. Some ancient thinkers believed infinity could not exist in nature. They saw it as a concept, an idea, not a real thing. Others believed that infinity had to be part of the universe, because it explained things that couldn't be explained any other way. In more recent times, the debate has continued. Some argue that actual infinities lead to paradoxes. If the universe is infinite, how do you talk about its total mass or energy? Can you compare sizes in an infinite set? What does it mean to say that something is infinitely far away? Others point out that infinities can be handled as long as we're careful. In math, There are rules for dealing with infinite sets. You can have bigger and smaller infinities. You can count some infinities, like the number of whole numbers. Others, like the points on a line, can't be counted in the same way. These ideas come from set theory, which gives us tools to think about infinity without falling into contradiction. But even if math can handle infinity, that doesn't mean nature does. Maybe the real universe only uses ideas that can be built from finite things. Maybe there's a maximum size, a maximum energy, a maximum amount of information. Some scientists have suggested that space itself might be made of tiny, finite pieces, like pixels on a screen. If so, then the universe might be large but not infinite. Maybe infinity is something that exists only in the questions we ask, and in the fact that no answer seems to be the last one. Edge cases. What would a literal boundary of the universe be like? The idea of the universe having an edge is something people have wondered about for centuries. It's a natural thought. Everything we deal with in daily life has edges: tables, houses, cities, even countries. So when we imagine the universe, it's hard not to picture it as a kind of giant object, floating in something else, with a wall or limit we could reach if we traveled far enough. But when it comes to the universe, that kind of thinking leads to strange and confusing questions. If the universe did have a literal edge, what would that even mean? Would it be like a wall where space just ends? Would it be a place beyond which there is nothing? Not empty space but no space at all? Not darkness, not vacuum, but something even stranger, the absence of existence? Or could there be something on the other side, another region, another kind of space, maybe even another universe? To think about this, we have to start with what we know. Right now, most scientists believe the universe doesn't have a boundary, but that's just one possibility. What if that's not how the universe works? What if space really is flat and infinite in every direction? That would mean there is no edge, because the universe just keeps going. You could pick any direction and travel forever, always finding more galaxies, more stars, more space. Still, there's no way to rule out something more unusual. So let's explore the stranger side of the question. What if there actually was an edge? If space had a physical boundary, the first question would be, what happens when you reach it? Do the laws of physics stop working? Does time stop? Would it be like hitting a wall, or would it be more like falling into something? If you approach the edge, what would you see? Would light reflect off it or vanish? Would matter be able to exist near the boundary, or would particles begin to behave unpredictably? Some theories in physics have tried to imagine a kind of edge, not as a hard wall, but as a transition zone, maybe where space breaks down, or where the familiar rules of our universe give way to something else. This idea is often used in multiverse theories, where the edge of our universe could be like the skin of a soap bubble, separating us from whatever lies outside. But that outside may not be space as we know it. It might not have time, dimensions, or any of the properties we rely on to describe things. It could be entirely different, a realm we don't have words or tools to describe. If the universe had a physical edge, you'd expect that things might be different near it. Gravity could behave oddly. Galaxies might start to thin out or change shape. The structure of the CMB could show signs of a limit, but we don't see any of that, as far as our instruments can see. That doesn't prove there's no edge, but it makes the idea harder to support. Still, the mind keeps returning to it. What would it feel like to approach the very edge of everything? If a spacecraft could somehow make the journey, what would the last few moments be like? Would space stretch thinner and thinner like a fading signal? Would time slow down? Would energy behave differently? Or would it all seem perfectly normal, right up until the moment you crossed over, if crossing over is even possible? One of the most challenging things about the idea of an edge is that it forces us to ask, what lies beyond? And the truth is, we might not have a good answer. Our brains aren't built to handle concepts like nothing, not empty, but non-existent. We keep imagining a void, or blackness, or a white screen stretching out endlessly. But all of those things are still something. If the universe ends, and there's nothing beyond, then what are we even describing? In classical geometry, an edge is a boundary between two regions. In our world, the edge of a table is where it stops and air begins. But with the universe, if it includes all of space and all of time, then there's nowhere for an edge to sit. There's nothing for it to be next to. One strange idea is that if the universe had an edge and you could get to it, you might find not an end, but a kind of restart. Maybe crossing the boundary would bring you into another region, a mirror universe, or a twisted copy of our own. Maybe space folds or tunnels into a different dimension. Maybe the edge is actually a gateway, not a stopping point. These are the kinds of possibilities that live in the outer edges of theoretical physics. And then there's the idea that the edge is not a place in space, but a place in time. In a sense, the Big Bang was a kind of edge, not in distance, but in time. We can't see beyond it because time itself didn't exist before. If the universe had a spatial edge, maybe it would work the same way. Not a wall you bump into, but a limit you approach, like trying to divide by zero. You get closer and closer, but never reach something that makes sense. The universe isn't a landscape sitting inside something bigger. It is the thing. It includes all the coordinates, all the directions, all the clocks. That makes the concept of an edge not just hard to reach, but hard to define. Still, the thought is hard to ignore. We keep coming back to it. We imagine brave explorers heading into the unknown, searching for the place where everything stops, because the idea stirs something deep inside, the need to understand where we are and what we're part of. Faster than light, would it let us see beyond the horizon? What if there was a way to move faster than light? Would it let us cross the cosmic horizon? Could we visit parts of the universe we aren't supposed to be able to reach? Could we look back in time or forward beyond the limits of observation? These questions lead us into a strange space between physics and imagination, where we start to wonder what's possible and what's simply not allowed. At first glance, it seems obvious. If you could go faster than light, you could simply zip past the cosmic horizon and explore whatever lies beyond. You could leave the bubble of what's visible and fly into the parts of the universe no telescope could ever detect. You could look back at Earth from the outside and maybe even send a message home faster than any beam of light could manage. It sounds like a perfect shortcut around the limitations of space, but things get complicated fast. According to Einstein's theory of relativity, faster-than-light motion brings strange consequences. Time starts behaving oddly. If something could go faster than light, it might also be able to go backward in time, depending on how you're moving and where you're observing from. This is a deep mathematical result of the equations that govern space and time. That's part of why the speed of light is treated as more than just a practical limit. It's tied into the structure of reality itself. There have been ideas, though, not direct violations of the speed of light, but ways to get around it by bending space. One of the most famous is called the warp drive. Instead of moving faster than light through space, the idea is to move space itself. A warp drive would contract space in front of a ship and expand it behind, carrying the ship along like a surfer on a wave. Because the ship isn't technically moving through space faster than light, it wouldn't break the rules of relativity. At least, not directly. Another idea is the wormhole. This is like a tunnel that connects two faraway points in space. If you could create or find one, you might be able to step from one side of the universe to the other instantly, like drawing a line between two dots on a folded piece of paper. Again, the ship isn't speeding through normal space. It's just taking a shortcut through a higher dimension. But both of these ideas come with problems. Huge ones. For a warp drive to work, you'd need something called negative energy, a kind of exotic matter that behaves in ways we don't see in everyday life. We're not even sure it can exist. And even if it could, the amount you'd need might be more than the entire energy of a star. With wormholes, the challenge is keeping them open. They tend to collapse the moment anything tries to pass through them. The same exotic energy might help, but again, it's purely theoretical. Still, let's say one of these ideas works. Let's say we really can build a faster-than-light ship. What would we find when we cross the cosmic horizon? The first thing to realize is that the regions beyond the horizon are still part of the same universe. They're not in another dimension or another reality. They're just far away. So if you could go there, you'd likely find galaxies just like the ones we know. Stars, dust, clusters, maybe even life. The universe doesn't seem to have changed its rules across space, so it's likely that those distant regions follow the same physics. But there's also the question of time. If you flew past the horizon, you wouldn't just be seeing distant space. You'd be seeing younger versions of it. You'd be diving into the past of those regions, catching up with light that hasn't yet had time to reach us. Depending on how fast you went, you might even get to see regions of the early universe that formed right after the Big Bang. You might observe the very first stars in places we could never see with any telescope. You might find pockets of the universe that evolved differently, just by chance, denser here, emptier there. Maybe even structures that challenge what we think we know about cosmic history. And if the universe is infinite, then faster-than-light travel wouldn't just show us more of the same. It could reveal versions of our own cosmic neighborhood, duplicates scattered across vast stretches of space. These are wild ideas, but they come straight from the logic of physics, stretched to its limits. There's one more twist. If you could travel faster than light, and if relativity holds true in its current form, then in some frames of reference, you'd be traveling back in time. That opens doors we may not want to open. Could you send a message into the past? Could you change events? Could faster-than-light travel allow paradoxes where cause and effect break down? Some physicists believe this is a hint that nature simply won't allow it. The laws of the universe may be designed to prevent these kinds of time loops from ever forming. Others think it may be possible, but only under special conditions. Maybe the early universe had shortcuts. Maybe distant galaxies are connected by deep structures in space-time that we haven't found yet. Even if faster-than-light travel remains impossible, the idea itself has value. It pushes us to think harder about what's out there. It reminds us that our view of the universe is limited, not because of imagination, but because of deep, built-in rules. And it challenges us to wonder whether those rules are final. The cosmic horizon stands as a kind of wall, and if we ever want to go beyond it, we'll have to find another way. Whether that's through physics we don't yet understand, or technologies we can't yet build, or simply deeper thinking about space and time, the dream of seeing beyond the horizon lives on. Wormholes as shortcuts to the unobservable. Wormholes are often described as tunnels or bridges through space-time. Because space can bend, twist and curve, it's possible, at least in theory, for two distant points to connect directly, like drawing a tunnel through the middle of a mountain instead of walking over it. A wormhole would be like that tunnel, linking two regions of space that are otherwise incredibly far apart. The idea isn't new. It dates back to the early work of Albert Einstein and Nathan Rosen in the 1930s. They noticed that the equations of general relativity allowed for solutions that looked like bridges between two separate places. These became known as Einstein-Rosen bridges. At first, they were seen as mathematical curiosities, not something that could exist in the real world. But over time, physicists began to wonder if these strange pathways could actually play a role in how the universe is built. A typical wormhole has two ends, or mouths, and a tunnel in between. One mouth could be here in our galaxy. The other could be on the opposite side of the universe, or in some versions, even in another universe entirely. If wormholes exist, and if they can be crossed, they would change everything. They would give us access to regions we could never hope to reach otherwise. They would turn the unobservable into the reachable. One of the most exciting possibilities is using wormholes to see beyond the cosmic horizon. No telescope can overcome that. But a wormhole doesn't rely on light. It would be a bridge cut through the structure of space-time itself. It wouldn't care about how far something is in terms of light travel time. If a wormhole connected us to a galaxy 50 billion light-years away, we could step through and be there instantly. If wormholes are possible, could they already be part of the universe? Could some galaxies be connected in ways we can't detect? Could matter or even information be moving through these hidden tunnels without us knowing? Some theories suggest that wormholes could exist naturally, perhaps left over from the earliest moments of the Big Bang. In those first fractions of a second, when the universe was still smoothing itself out, tiny fluctuations could have created wrinkles in space-time. Some of these might have stretched into stable wormholes. The problem is, they wouldn't last long. A wormhole, by default, tends to collapse as soon as it forms. The gravitational forces pull it shut, cutting off the connection before anything can pass through. To keep a wormhole open, something strange is needed, something that pushes outward instead of pulling inward. Physicists call this exotic matter. It's not antimatter. It's a form of energy that has negative pressure. It would act like a balloon inside the tunnel, holding it open against gravity. We don't know if this kind of matter exists. In theory, it could be related to the vacuum energy of space, or to some yet undiscovered field. We see hints of similar effects in quantum physics, like the Casimir effect, where a vacuum can exert pressure in odd ways. But turning that into something that could stabilize a wormhole is far beyond anything we can build or test today. In some versions of string theory, wormholes arise naturally from the way extra dimensions are shaped. In the world of quantum gravity, they might appear as shortcuts, linking different patches of space-time at the smallest scales. Some researchers have even proposed that wormholes and entanglement, the strange connection between quantum particles, might be different sides of the same coin. If that's true, the entire universe might be threaded with connections we can't see. Let's imagine for a moment that one of these wormholes opens up near us. The mouth could look like a shimmering sphere, or perhaps an area of space that bends light in odd ways. If you approached it, you might feel nothing unusual, but stepping inside would be like slipping between the pages of a book. You'd pass through the tunnel, and in an instant, you'd emerge somewhere else. From that vantage point, everything changes. You'd be looking back at a different part of the cosmos, shaped by different conditions. Maybe the density of matter is different there. Maybe the stars formed earlier or later. Maybe there are no galaxies at all, just vast clouds of gas still waiting to collapse. You could look back toward your starting point and see Earth's galaxy as a faint point of light. Wormholes, if they exist, wouldn't just be travel devices. They would be tools of discovery. They would let us test our theories of space and time, of gravity and matter. They might even let us search for signs of life in places we could never reach with traditional methods. And if we ever learned how to control them, to create them, stabilize them, and aim them, they could change how we think about isolation in the universe. But there are dangers too. A wormhole might be unstable. A slight disturbance could cause it to collapse, trapping or destroying anything inside. The connection between two regions of space might not be smooth. It might be twisted by strange gravitational effects, or filled with high-energy radiation. And then there's the question of paradoxes. If a wormhole lets you move between two distant places faster than light, could it also let you send signals into the past? Could you interfere with your own history? Some physicists think nature has built-in protections, which they call the chronology protection conjecture, the idea that time travel is forbidden, not by laws we invent, but by the very fabric of reality. Others argue that certain kinds of wormholes could exist without leading to contradictions, especially if they're one-way only, or if time behaves differently inside. In a universe filled with mysteries, wormholes offer one of the most daring. They are not magic portals, but real possibilities hidden in the math of space-time. Whether they exist or not, they inspire questions about distance, connection, and whether the farthest reaches of the cosmos are really out of reach at all. Would a hyper-advanced civilization be able to map the whole universe? Could a civilization far more advanced than ours, perhaps one that has existed for millions or even billions of years, find a way to map the entire universe, even the parts we can't see? Our own species is just beginning to understand the limits of what can be observed. We've built telescopes that can peer back over 13 billion years. We've launched spacecraft that have just barely passed into interstellar space. But compared to the scale of the universe, our reach is still tiny. The rest of the cosmos lies beyond, unreachable by any signal we could ever send or receive. But what about a species that has had not just thousands of years, but eons to explore and advance? What could they see? What could they build? To begin imagining this, it helps to consider how a truly ancient civilization might grow. If life emerged early enough, perhaps just a few 100 million years after the Big Bang, such a civilization would have had an incredible head start. Over time, they might have spread across their galaxy, mastering energy, matter, and perhaps even space-time itself. They would have passed through the kind of technological steps that we can only dream about. They might not use rockets, satellites, or radio waves. They might have developed entirely new ways to manipulate the universe, methods so different from ours that we wouldn't even recognize them as technology. But even with all that power, they'd still face the same basic barrier we do. So would even a super advanced civilization be stuck like we are? Maybe not. If such a civilization found a way to beat the expansion of space, they might be able to reach beyond the observable universe. If they could reach those far-off regions, they could gather information directly, bringing it back to their part of space, slowly building a map not just of what's visible, but of everything that exists. It's also possible they wouldn't need to go anywhere. They might be able to infer what lies beyond by using data we can't even collect. Humans use the CMB to learn about the early universe, but we're limited by our tools and by the resolution of our measurements. An ancient civilization, however, might be able to decode much more from these signals, finding patterns in the background noise that we miss. Or maybe they've built instruments that can detect other forms of radiation, or other fields entirely, things we don't even know exist. Another path might involve artificial intelligence. Not the kind we're building now, but machines so intelligent and capable that they could model the universe from first principles. Imagine a system that knows every law of physics, every particle, every field. It could simulate vast regions of space, not just as guesses, but as accurate reflections of what's actually out there. If these simulations are refined by real data, gathered over millions of years, the result might be the next best thing to seeing the unseeable. There's also the idea of spreading out, not just through one galaxy, but many. An advanced civilization might send probes, not at light speed, but at some fraction of it, toward different galaxies. These probes could be tiny, self-replicating machines that build copies of themselves, using local resources. Over billions of years, they could fill large regions of the cosmos, each sending back data. If this civilization started early enough, they could have outpaced the horizon, reaching galaxies that are now forever lost to us. In a sense, they'd be leaving footprints across time, gathering light before it disappears from view. But even this raises limits. The universe is not just expanding, it's accelerating. Unless this advanced species started their journey early, even they would be shut out from parts of the universe. And the farther out you try to go, the more unreachable it becomes. Could such a civilization map all of it? Maybe not. But maybe their idea of all is different. They might think of the universe not as something to be fully seen, but something to be understood. They might use patterns in quantum fluctuations or the properties of cosmic fields to learn what lies beyond direct observation. They might detect signs of other civilizations, faint whispers left in radiation or encoded in the alignment of galaxies. If life is common, and if these beings communicate across great distances, the universe might already be crisscrossed with signals too subtle for us to detect. But to them, it would be like a vast web of connection, a shared map created by many voices. And then there's the idea of dimensions. We live in a universe with 3 dimensions of space and 1 of time, but some theories suggest there could be more. An older civilization might have learned how to access or perceive these hidden dimensions. If so, they could look at the universe not just as a line or a sphere, but as a shape with sides we can't imagine. From that higher view, our cosmic horizon might look like just a curve on a surface, something that can be stepped over or folded around. From that place, mapping the whole universe might be no harder than mapping a mountain range is for us today. It's tempting to think of such a civilization as godlike, all-seeing, all-knowing. But perhaps they too face mysteries. Maybe the universe is infinite, or perhaps it loops in ways even they can't trace. Maybe there are regions so strange, so different in structure or law, that no signal can pass between them. There might be domains of space that are truly unreachable. In that case, even the most powerful minds might hit a wall. Mapping the cosmos is not just about distance or speed, but about how we understand space, time, and information. A hyper-advanced civilization, whether real or only imagined, pushes us to think bigger. It asks us to question the limits we've accepted and to wonder what might lie beyond them. Not just galaxies and stars, but entire ways of seeing, knowing, and exploring. Could time travel reveal what's outside the universe? In Einstein's theory of relativity, space and time are part of the same thing, space-time. They aren't completely separate. When you move faster through space, you move slower through time, and vice versa. Satellites in orbit experience time slightly differently than clocks on Earth. If you're near something with a lot of gravity, time ticks slower. These small effects are measurable and real. So time isn't just a background we live in. It bends and flows depending on motion and mass. Now, imagine if we could somehow push these effects to the extreme. What if we could create a situation where time didn't just tick more slowly, but could be rewound or skipped altogether? Some theories suggest that with enough energy, or in the right kind of curved space-time, time loops could form. These are called closed time-like curves. They're like paths that twist back on themselves, letting you return to an earlier point in time, but they're incredibly unstable and probably impossible to build. Still, the idea lingers. If we had a way to move back in time, we could observe the early universe up close. Right now, we can only see it by collecting ancient light. But imagine being able to go there directly, to stand in the moments after the Big Bang and watch the first galaxies form. Maybe you'd be able to see structures that are now too far away. Maybe you'd see what's hidden behind the cosmic horizon, not by moving across space, but by going back to a time when space was smaller and all regions were closer together. In that sense, time travel could act like a telescope more powerful than any we've built. Instead of waiting for light to arrive, you'd go to the moment when the light was first created. Of course, that assumes you could survive such a trip. The early universe was dense and hot, so extreme that matter as we know it hadn't even formed yet. You wouldn't find stars or planets, but a sea of particles and energy boiling and colliding. What about traveling forward in time? That might offer a different kind of view. As time goes on, more light from the distant universe reaches us. The observable horizon gets wider. So if you could jump ahead a few billion years, you'd be able to see galaxies that are currently hidden, simply because their light hasn't arrived yet. But there's a limit to this, and there are galaxies whose light will never reach us. So moving forward in time doesn't mean we'll eventually see everything. But perhaps, in some future age, an advanced civilization could use time travel not just to observe space, but to access places outside it. If time is different in each multiversal bubble, then moving between them might involve shifting through time as well as space. Maybe these transitions are only possible at certain energy levels. Of course, none of this is proven. It may turn out that time is one-directional, and that there's no going backward, no shortcut to other realities. But some scientists still explore the possibilities. They ask whether time travel might be hidden in the mathematics of quantum theory, or buried in the properties of black holes. Some say that inside a black hole, time and space flip roles, and that falling into one might be a kind of trip to the edge of time itself. But what lies beyond that edge is unknown. Is it a dead end, a crunch, or a passage into something else, some other region, some other beginning? Another question is whether time travel is really a trip in the usual sense. Some theories suggest that all times exist at once, that the past, present, and future are all part of a larger structure, like frames in a film. We experience them one by one, but they're all there. If that's true, then maybe what lies beyond our universe isn't far away in space, but in a different part of time. And if we could find a way to access those other parts, we might learn things that are forever out of reach from our current moment. But even if we can't travel through time physically, there's another way it might help us explore, through memory and record. Light, in a way, is a form of time travel. When we look at distant stars, we see them not as they are now, but as they were long ago. Every photon that reaches us is carrying information from the past. The farther it's traveled, the older that information is. So in a very real sense, the universe is constantly sending us messages from earlier times. If we learn how to read those messages better, if we build instruments that can capture the faintest echoes, we may uncover parts of the universe that feel like time travel, even without moving. Would a multiversal voyage be theoretically possible? While we have no proof that a multiversal voyage is possible, there are strange corners of theoretical physics that leave the door open, even if just a crack. First, there's the question of what we even mean by another universe. In science today, the word multiverse can mean many things. Sometimes it means other bubbles like ours that formed during inflation, each with different properties or physical laws. Other times it refers to quantum worlds, branches that split off each time a choice is made or a particle is measured. Some versions of string theory even suggest extra dimensions folded up tightly all around us, possibly containing entire realities we never see. If these places really exist, could we ever get there? A trip between universes, if it's possible at all, would need more than just a spaceship. It would need some kind of bridge through the deep structure of space and time. A wormhole might just be able to connect not just two places in the same universe, but two entirely separate universes. Assuming we could somehow create or stabilize a wormhole, we'd still need to find out where it goes. If it leads to another part of our universe, that's impressive enough. But if it leads to a completely separate universe, that would change everything. But we have no way to test whether wormholes really go anywhere. Even if they exist, we don't know if you could send anything through them without destroying it. The forces near a wormhole's mouth could tear apart atoms, let alone spaceships. Another extreme idea comes from brain world theories. These suggest that our universe might be like a sheet, or brain, floating in a higher dimensional space. Other sheets could exist nearby, separated by a dimension we can't see. It's a bit like pages in a book. Each page is its own world, but they're close together. In these models, gravity might leak between brains, which is one way scientists have tried to explain why gravity is so weak compared to the other forces. If that's true, maybe there are ways to interact with other brains. Maybe a strong enough pulse of energy, or the right kind of particle, could push through the gap. But jumping from one brain to another would be like falling off the edge of our reality. It's not just about going sideways, it's about going into a hidden direction, one we don't experience. That would require technology we can barely imagine. We'd need machines that can manipulate the very shape of space, or that can generate fields stronger than anything we've ever made, and even then, we wouldn't know what we were stepping into. The laws of physics in another brain might be wildly different. Time might flow differently. Particles might behave in ways that would be deadly to the very matter of our universe. There are also ideas from quantum physics that hint at possible multiverse travel, though in a more subtle way. In the many worlds interpretation of quantum mechanics, every possible outcome of every event happens, each in its own branch of reality. In this view, there are countless versions of us, living out every possible choice and chance. But these branches don't normally talk to each other. They're like trains on separate tracks, never crossing. Some researchers wonder whether it's possible to cause interference between branches, like waves overlapping. That might allow for some kind of message to pass between them, or, in the most far-out cases, for matter to shift from one to another. This would require tampering with quantum coherence on scales far beyond anything we've ever done. In the lab, we can keep a few particles in quantum states for brief moments. But to bridge entire branches of reality, you'd need to scale that up, holding trillions of particles in perfect alignment while performing delicate operations that don't destroy the wave function. It's like trying to balance a soap bubble the size of a mountain. One wrong move, and it pops. According to certain theories, when a black hole forms, the collapse creates not just a singularity, but a passage to a new universe on the other side. In this view, every black hole could be a kind of cosmic seed, giving birth to its own space and time. If that's true, then our universe may have been born from a black hole in some parent universe. And perhaps we too are giving birth to others. But even if this happens, we don't know if anything from our side can survive the journey. The conditions near a black hole are so extreme that nothing seems to escape once it crosses the event horizon. And then there are the speculative ideas that combine quantum computing, artificial intelligence, and space-time engineering. Some theorists imagine civilizations so advanced that they could simulate entire universes, or even build new ones. In such a scenario, travel might not be physical at all. It might be informational. Consciousness could be copied into a new structure, or booted up inside a synthetic universe. If that's possible, then visiting another universe could be more like logging into another server, provided you know the access code and the rules of the system. Of course, we are nowhere near this level of technology. Right now, we're still struggling to send small spacecraft beyond our own solar system. The thought of jumping to other universes is so far beyond our reach that it feels almost like myth. But that hasn't stopped scientists from asking the questions. They draw up models, run simulations, and look for any sign, no matter how faint, that points to something beyond our own cosmic bubble. Maybe, far in the future, some breakthrough will change everything. Maybe we'll find signs of quantum fluctuations that hint at other realities. Maybe we'll learn to shape gravity or open pathways through higher dimensions. Or maybe we'll simply discover that we are alone in a single universe and that the dream of multiversal travel will remain a dream. How will the universe end if it's infinite? If the universe is truly infinite, it may fade slowly over unthinkable amounts of time until it becomes something cold, dark, and still. This is the idea behind the Big Freeze. Everything keeps moving apart. Galaxies drift away from each other. Energy spreads out, thinner and thinner. Space itself keeps stretching, but nothing new is created. Over time, the universe becomes more empty, more quiet, and more lifeless. There's no explosion, no bright moment, just a long decline into darkness. In a universe like this, time doesn't stop, but change does. Stars die, and no new ones are born. Planets freeze, black holes slowly evaporate, even atoms fall apart in the far future. It all happens incredibly slowly, over trillions upon trillions of years. The process just continues, like a clock that never runs out of time but ticks more quietly with every step. This idea of a forever slow ending raises strange thoughts. What does it mean for a universe to go on without anything happening? If time still passes, but nothing changes, does time still matter? It's a strange kind of eternity, not full of light and activity, but of dimness and decay. In an infinite universe, this kind of ending becomes even more curious. If the universe goes on forever in space and also forever in time, then this slow freezing doesn't happen all at once. Different regions of the universe may reach the end at different times. One area might still have stars while another is already dark. The whole universe doesn't switch off. Instead, it fades bit by bit, like a fire dying out in a field so wide that no one can see the edges. But some theories suggest that the very fabric of space might not be stable forever. It could undergo something called vacuum decay. In this idea, the universe sits in a kind of false stability. It feels stable, but it isn't truly at the lowest energy it could be. At any moment, a small patch of space might suddenly shift to a more stable state. If that happens, it could create a bubble of new physics. This bubble would grow at nearly the speed of light, wiping out everything in its path. Nothing could stop it. It wouldn't be painful or explosive. It would just erase the familiar rules of space and time. This might never happen, or it might be happening already, far away, racing toward us. We wouldn't see it coming, but if it did happen, it would be a very different kind of ending. Not slow and cold, but sudden and final. Still, most predictions point to the slow end, the big freeze. It's based on what we see today: expansion, entropy, cooling, and the fading of light. This ending doesn't need anything to go wrong. It just needs time. Enough time for stars to die, for galaxies to empty, for black holes to vanish. Enough time for even the most energetic particles to stop moving, for even the smallest bits of warmth to fade away. The idea of an infinite universe decaying slowly doesn't give us a neat ending. Instead, it gives us a kind of quiet horizon, always receding. It asks us to imagine time not in years or centuries, but in stretches so long that numbers become meaningless. It's hard to picture a universe that fades, a universe that forgets itself, that grows so wide and so cold that even memory disappears. But that might be what lies ahead if the universe is infinite, not a sudden end, but a long silence. How will the universe end if it's finite? If the universe has a limit in size, its ending might also be more final, and much more dramatic. One possibility is the Big Crunch. This is the idea that the expansion of the universe could eventually slow down and reverse. Instead of galaxies flying apart forever, gravity could pull everything back together. It's like a ball thrown into the air. It goes up, slows down, and then falls back down. If the universe had just the right amount of matter, enough for gravity to win against the outward push, then the whole cosmos could begin to contract. The entire universe would shrink, growing hotter and denser as everything packed into a smaller and smaller space. Over time, this process would speed up. Just as the expansion of the universe grew faster over billions of years, the collapse could grow more intense. Eventually, the whole universe could shrink down to something incredibly dense and hot, perhaps even a single point, like the one that began the universe in the Big Bang. But this would be the reverse, not a beginning, but an end. The Big Crunch would erase structure. Galaxies, stars, atoms, everything would break down into pure energy. It would be violent, fiery, and final. In this scenario, time itself might come to a stop. As everything collapses, the very fabric of space could tear or fold. Some wonder if time and space would vanish completely. Others ask if this could be the trigger for a new beginning, a new universe born from the ashes of the old one. This idea connects the end to a possible rebirth, like a cosmic cycle of bangs and crunches. There's also the idea of a big rip, a different kind of dramatic end. This one doesn't depend on the universe being infinite or finite, but its effects might be more noticeable in a finite universe. The big rip would happen if dark energy keeps getting stronger. Right now, dark energy is making galaxies move away from each other faster and faster. But if this force keeps growing, it could eventually pull everything apart, even things held together by strong gravity. Galaxies would stretch and break, then stars, then planets, then atoms. Even the smallest particles could be torn apart. Time would reach a final moment when the fabric of the universe itself would split open. The big rip would be total. It wouldn't just remove structure, it would remove the idea of space itself. A finite universe might also collapse simply because of internal instability. Some theories suggest that space might not be completely uniform. If there's a flaw, even a small one, it could grow over time. Like a crack in glass, this flaw could spread until the entire structure of space-time gives way. It's hard to imagine, but the universe might be held together by a balance that isn't permanent. If that balance shifts, The result could be sudden and absolute. All of these ideas share something in common, that a finite universe could end with a kind of finality that an infinite one never reaches. A beginning and an end, like a story with a clear start and a final page. We're still learning about dark energy, about the shape of space, and about how the rules of physics behave at extremes. But every piece of new data changes the picture a little. Every measurement of the universe's rate of expansion, every experiment in particle physics, all of it brings us closer to knowing how the story might end. There's something both terrifying and beautiful about imagining the universe's final act. If it is finite, then maybe it's like a candle. It burns for a while. It gives off light and warmth, and then it goes out. But maybe, just maybe, it lights another, a cosmic rebirth. Even a dramatic ending might not be the end, just a transformation. Is the cosmic horizon like the edge of a game map? In many modern video games, players explore wide-open landscapes that seem to stretch out endlessly. Forests, mountains, oceans, they all appear to go on as far as the eye can see. But behind the scenes, something interesting is happening. The game's software doesn't load or render everything at once. It only draws the part of the world that the player can actually see or is about to reach. Everything outside that area either doesn't exist yet or exists in a simpler form, ready to be filled in later. This saves memory, avoids slowdowns, and keeps the game running smoothly. It's an invisible trick, and some scientists and philosophers have wondered, what if something similar is going on with the universe? The idea starts with the fact that we can only observe a limited portion of the cosmos. It's a hard boundary set by light. Beyond it, the universe might go on, or it might not. We have no way to know. So is that all there is? Is the rest of the universe really out there, waiting to be seen? Or is it more like a video game map, where the universe only draws the parts that are needed for us to observe? Could it be that the cosmos isn't a fully finished product, but more of a responsive system, one that reacts to the presence of an observer? This kind of thinking brushes up against some very deep and strange ideas. In quantum mechanics, there's a concept called the observer effect. It's not about consciousness directly causing things to happen, as it's sometimes misunderstood. But it does say that certain properties of particles, like their position or momentum, aren't settled until they're measured. Before that, they exist as probabilities. This idea has led some to speculate that, at the deepest level, reality might be incomplete without something interacting with it. If we take this concept and stretch it to a cosmic scale, we might wonder whether the universe itself renders only what is necessary for experience. That would make the cosmic horizon not just a practical limit, but a kind of logical boundary, like the edges of a simulation that isn't built beyond what's needed. It sounds outrageous, but it's not entirely without precedent in theoretical work. Some scientists have explored the idea of a simulated universe. This doesn't mean a cartoon world or something made on a laptop. It means that reality, at its core, could be made of information, like a computer program. Space, time, matter, everything could emerge from the behavior of a deep code running on an unknown substrate. In this view, the universe acts like a simulation, not because it's fake, but because it operates by processing data. And just like a simulation, it might not calculate things that aren't needed yet. There are even proposals in quantum cosmology that suggest something similar. In some models, the universe's wave function doesn't collapse into a definite form until an observation is made. That doesn't mean nothing exists before we look at it, but it may mean that the fine details don't fully emerge until they become part of a measurable chain of events. This would make the edge of the observable universe not just a place beyond which we cannot see, but a kind of resolution limit. A border, not just of distance, but of information. Of course, most physicists believe the universe exists independently of whether we observe it or not. The cosmic horizon, in this standard view, is not a hard wall or a foggy edge. It's simply a limit imposed by time and light. Beyond it, space continues. Galaxies keep forming and evolving. But even in this more grounded version, the cosmic horizon still acts like a kind of game map boundary because we are limited in what we can ever know. The effect is the same. Our view is surrounded by a moving edge. As time passes, the horizon expands, we see more. But the farthest regions we once hoped to observe are moving away faster than the light they send out. They slip beyond our reach, like parts of a map that are deleted from the game as you walk away. Like a player stuck in one zone of a giant open-world game, we are confined to our own corner. This has led some scientists to wonder whether the universe is observer-specific in some way. If we could move fast enough or find some way to leap beyond the horizon, we might see parts of the cosmos that haven't been loaded yet. But even this may not be possible. The rules of space-time appear fixed. No signal can move faster than light. No observer can outrun the expansion itself. The boundaries aren't just hard to cross, they may be built into the very logic of the universe. Yet the comparison to a game map still helps us think about the problem. In both cases, there's an edge made of technical limits. In games, it's about memory and processing power. In cosmology, it's about light, time, and geometry. Both systems show us that limits don't always mean endings. Sometimes they mean transitions, zones where knowledge fades into uncertainty. If the universe is like a game map, then we are characters living inside a space that feels enormous, yet may be defined by deeper rules. The game never reveals its full code to the player. You experience only what's rendered in your path. Maybe the cosmos is the same. Maybe what lies beyond the cosmic horizon is not only invisible, but unknowable by design. Some have tried to test this. Physicists have searched for signs that our part of the universe is different from what's beyond. Perhaps a signal from another bubble universe, or a strange patch of sky that hints at a boundary. Every new instrument, every deeper scan, pushes that rendering limit just a little farther. If the universe has an edge, who or what put it there? Some people, when faced with the idea of an edge, ask whether it points to something beyond science. Maybe a creator, a designer, or a force outside the universe itself. After all, if the universe is all of space and time, and it has an edge, then whatever lies beyond must be outside of space and time. That sounds like a definition of something supernatural or divine. It's easy to see why this kind of thinking appears. When people come to the edge of knowledge, they often ask if someone else built the world they're inside. Not because science can't go further, but because the shape of the question begins to shift. It's no longer just how big is the universe, but why is there a universe at all? In the past, many cultures believed that the world had a beginning and an end, set by a higher power. Creation stories often describe the earth as a flat surface with borders, surrounded by chaos or guarded by gods. As science advanced, it changed how we see those stories. But the instinct to look for purpose hasn't gone away. In the modern age, the Big Bang Theory tells us that the universe had a beginning. It says that space and time themselves came into existence about 13.8 billion years ago. But it doesn't tell us what happened before that, or whether before even makes sense. And it doesn't tell us why it happened, or what set it in motion. If there's a limit to the universe in space, just like there was a limit in time, then the same mystery returns. What lies outside? What was the reason? Why is there something rather than nothing? Some physicists try to answer this with ideas from quantum theory or cosmology. They talk about vacuum fluctuations, multiverses, and mathematical models. Maybe the universe came from a random fluctuation in a larger space. Maybe it bubbled into being from a sea of possibilities. Maybe it's one of countless others, all born from a deeper rule set we don't understand yet. But these explanations, as detailed as they are, don't always satisfy the deeper question. Because even if we say the universe came from something more fundamental, we can still ask, where did that come from? Who or what set the stage? And if we imagine the universe as a limited object, then we're forced to imagine something that is not the universe. Something else. For some, that something else is God, or a creative force that made space, time, and the rules of reality. For others, the edge itself is just a sign that we don't understand the whole picture. Maybe our minds are trying to push a question too far, asking things that don't make sense outside the system we live in, like asking what's north of the North Pole. And yet, even that comparison has its limits. Because the North Pole is still on a surface. It belongs to Earth. If the universe is the totality of everything, and it has an edge, then what is beyond that edge is not part of everything. That's what makes the question so hard to let go of. There are scientists who say we should not ask what's beyond the universe because the universe is all there is, that the question is meaningless, but others are not so sure. They say that curiosity doesn't stop at a boundary, it climbs over it. If we reach a cosmic edge, they say, we have a right to ask what built it, and whether the rules that hold inside the universe, like space, time, and energy, are the only rules that exist. Maybe the outside is not nothing, but something we can't detect, a deeper level of reality. Some have even compared this to ideas in ancient philosophy or theology, worlds beyond worlds, layers of being, or a grand intelligence behind the scenes. These are not the kinds of ideas you can test with a particle accelerator, but that doesn't mean they're useless. If the universe does have an edge, it might challenge the very way we define existence. We're used to thinking of things as having causes and boundaries, but if space and time themselves had a beginning and an end, then our normal tools for asking why might not work anymore. Still, it's hard not to wonder. If there's a wall out there, a final limit, did something or someone place it there? If the universe is a structure, is it like a painting with a canvas? Like a building with walls? And if so, who made the blueprint? These aren't questions with easy answers. They don't lead to experiments or neat equations, but they do lead us to the edge of thought. Science, as powerful as it is, still exists inside a larger human story, a story of wonder, fear, and longing to understand. At the edge of the universe, we're not just looking for stars and galaxies, we're looking for meaning. Holographic universe. Could the cosmos be a 3D illusion? The holographic principle suggests that the three-dimensional world we live in, full of people, planets, galaxies, and light, might actually be a kind of illusion. According to this idea, everything we experience in 3D space could be a projection, much like a hologram. In other words, the real information that makes up the universe might live on a two-dimensional surface somewhere else. This is a serious idea being discussed in some of the most respected physics departments in the world. It came out of an effort to understand black holes. When scientists studied what happens to information that falls into a black hole, they ran into a problem. According to one view, the information should be destroyed, but that goes against a basic rule of physics, that information can't simply vanish. This puzzle got deeper when researchers realized that the amount of information inside a black hole seemed to match the area of its surface, not its volume. That's unusual. You'd expect the amount of stuff inside a box to depend on how big the box is on the inside, not how much area it has on the outside. But with black holes, it was different. The information, the bits and pieces that describe everything inside, seemed to live on the surface of the event horizon, the invisible boundary around the black hole. If this is true for black holes, could it also be true for the universe itself? This is where the holographic principle comes in. The idea is that all the information in our 3D universe, every atom, every star, even our thoughts, might be stored like a kind of cosmic code on a distant two-dimensional surface. What we see and feel as 3D might be a kind of projection, the same way a 3D image can be made from a flat hologram. To be clear, this isn't saying the universe is fake or that we're living in a dream. It's more like saying the basic rules and patterns that form our world might be written in a lower dimension, just like the pixels on a screen can show a 3D video, even though the screen itself is flat. From where we stand, everything feels solid and real, but that might be because we're inside the projection. We can't see the source code. We can only live inside the world it creates. This idea is hard to picture. Most of us are used to thinking in terms of space that we can walk through and touch. But imagine holding a holographic sticker in your hand. If you shine light on it the right way, you'll see a 3D image appear, even though the surface of the sticker is flat. The image looks like it has depth, shape, and texture, but it's not really there. It's created by patterns on the surface. Now imagine that sticker being the entire universe. The patterns on the edge, the boundary of space, might hold the true description of reality, and the world we move through, with length, width, and height, might be the result of that deeper surface. One way to think about this is to imagine a giant sphere. The surface of the sphere is two-dimensional, like the skin of a balloon, but from this surface, the full 3D space inside the balloon is created. The information on the outer layer encodes what happens inside. We're inside the balloon, living in the 3D projection, while the true data that makes up reality sits on the outer skin. In some versions of string theory, the holographic principle comes up naturally. These theories suggest that the universe we live in might follow rules that come from a lower dimensional space. We're not sure where this lower dimensional space is or what it looks like, but the equations support the possibility. What makes this idea even stranger is that it could help solve some big problems in physics. For example, combining gravity and quantum mechanics has been one of the hardest challenges in science. Gravity works on large scales like planets and stars. Quantum mechanics works on tiny scales like atoms and particles, but they don't fit together easily. The holographic principle might offer a way to bridge the two by showing that gravity in a 3D world could come from simpler forces in a 2D one. If the universe is a projection, then space itself might not be fundamental. It could be something that appears only when the right conditions are met, like a shadow cast on a wall. Time too might be part of the illusion, built into the way the projection unfolds. These ideas go against our senses, but nature doesn't always follow what feels natural. There's another strange consequence of this idea. If everything is encoded on a distant surface, then that surface might hold the complete story of the universe, even parts we can't see. The faraway galaxies that are too distant for our telescopes, the dark matter we can't touch, and even the patterns of our thoughts might be linked to something written at the boundary. In a strange way, it's like saying the universe has a memory, a record of everything that has ever happened, stored on its outer skin. Some physicists think we might one day be able to test this idea. Some look at black holes, where the math of the holographic principle is strongest, and hope to find signs that match the predictions. Still, much of this remains theory. If this idea is right, then our everyday world is only part of the story. The universe we walk through might be like the image on a movie screen, rich, detailed, and lifelike, but created by something simpler behind the scenes. And just like in a hologram, each part of the image might carry a piece of the whole, hinting at connections we don't yet see. Would knowing the universe has an edge change science forever? If scientists ever discovered a real edge to the universe, an actual boundary where space stops, it would be one of the most important events in human history, not just for astronomy or cosmology, but for all of science. For thousands of years, people have wondered about the size and shape of the universe. If one day we found proof of a boundary, it would mean that almost everything we thought we understood would have to be re-examined. The first field to feel the impact would be cosmology. That's the science that tries to explain the structure and history of the universe. Right now, the most accepted idea is that the universe has no edge. If that changed, if we detected a place beyond which nothing exists, it would throw that entire framework into question. We would have to revisit the basic models of how the universe formed, what it's made of, and how it behaves on large scales. Much of modern cosmology depends on the idea of isotropy. If there's an edge, that symmetry is broken. It would mean the universe has a shape that isn't equal everywhere. That might seem like a small detail, but it would affect everything from how galaxies are distributed to how light travels across space. We would need to rewrite our models of cosmic expansion. The equations that describe how galaxies move, how time flows, and how energy spreads would all need to account for this new boundary. Physics as a whole would also be shaken. For over 100 years, physicists have based their work on theories like general relativity and quantum mechanics. These theories are built on the idea that space-time is smooth and continuous. They don't make room for a wall at the edge of reality. If a boundary exists, it might mean that the laws of physics themselves are different near that edge. If that's true, then the theories we've used to build things, from satellites to particle accelerators, might not tell the whole story. We would be forced to go deeper, to find new rules that work not just here, but everywhere. Some scientists might ask whether the edge is physical or something more abstract. Is it a solid wall, like the surface of a sphere? Or is it just the limit of space itself, beyond which nothing exists? If it's the latter, then we may face new kinds of questions. For example, how does energy behave when it reaches this limit? Can particles bounce off it? Do waves reflect, scatter, or vanish? These are questions we've never had to ask before because we've never had reason to believe such a boundary existed. Astronomy would face a new kind of challenge. Until now, we've studied the universe by looking outward. Telescopes capture light that has traveled for billions of years. We map galaxies, stars, and distant radiation. But if we knew there was an actual limit, an outer wall where space ends, we would begin to focus on that edge. We'd want to know what it looks like, how far away it is, and whether it can be reached. Our search for exoplanets or distant supernovae might become less important than trying to understand what lies at the boundary. New kinds of instruments would be designed just to study that region. Space agencies might shift their goals from planetary exploration to edge detection. Many of our ideas about the past and future come from the idea of symmetry. The universe looks about the same in every direction, so time seems to move forward in a steady way. But if space has a limit, does time have one too? Is there a beginning and an end not just in size but in duration? Would time stop at the edge? Or would it continue somewhere beyond? These questions would push physicists and philosophers into new territory. They would have to develop new theories of time. Math is often thought of as abstract and universal, but a discovery like this would test that idea. Much of modern math assumes an infinite space, or at least one without hard edges. Calculus, geometry, and many forms of algebra are based on smooth curves, continuous spaces, and limitless sets. If the universe has a boundary, then we may need new kinds of math to describe it. The edge might involve sharp discontinuities, new topologies, or limits we've never had to handle before. Mathematicians might develop new branches of logic and structure just to cope with this change in how reality behaves. There would also be new debates about what lies beyond the edge. Is it truly nothing, an absence of all matter, energy, and dimensions? Or is it the edge of a larger structure we can't yet see? These questions would bring in ideas from string theory, brain theory, and quantum gravity. Some of these theories already suggest our universe could be a bubble inside a higher dimensional space. If we found an edge, those ideas might move from the fringe to the center of science. We might even begin to think of the universe as something embedded in a bigger framework, like a dot on a sheet or a fish in a tank. The idea of a cosmic boundary touches on questions that are as old as human thought. What is the nature of reality? What lies beyond the known? Are there things we're not meant to see? These were once questions for religion and myth, but with real data showing a cosmic edge, scientists would now be dealing with them too. It might not be long before physicists are writing papers on the nature of nothingness or the meaning of beyond. The human response would be just as powerful. Artists, writers, and thinkers would begin to reflect on what it means to live in a bounded universe. The discovery of a limit would raise new questions about freedom, exploration, and existence. Would we still dream of traveling forever, if forever turns out to be a wall? Would people feel trapped in a cosmic container, or more secure, knowing there is a boundary. Some would also wonder if the edge was put there on purpose. If there is a boundary, could it have been created? That question could bring in the idea of design, or simulation, or intelligence behind the structure of the universe. While science tries to stay away from those ideas without evidence, a clear and undeniable edge might force them into the conversation. Even scientists who don't usually think in terms of purpose or plan would have to admit that the universe appears more structured than we thought. We would also need to think about how we teach science. School textbooks would have to change. University courses would be rewritten. The story of the universe, once told as a tale of endless space and eternal expansion, would have to be updated. New generations of scientists would grow up in a world where the universe isn't infinite, but something with a border, a frame, or even a surface. There might also be practical uses. If the edge is real and reachable, we might one day try to send probes toward it. Could we use it as a kind of observatory? Could we learn something about other universes, or different laws of physics, just by studying that line? In time, the edge of the universe might become the most studied area in all of science. Everything we know about motion, light, gravity, time, energy, and even logic would be touched by the discovery of an edge. It would not be a simple detail. It would change the very foundation of what we think the universe is. Simulation hypothesis. Are we staring at the limits of the program? As we build more realistic video games and virtual environments, it becomes harder to ignore the question, if we can do it, could someone else, more advanced than us, have done it first? Could our universe be something they built? Why is the universe so perfectly balanced for life? Why do the laws of physics work so well, yet seem so fine-tuned? Why are the patterns we see, from galaxies down to atoms, so strangely ordered? If someone were designing a reality, these are exactly the kinds of things you'd expect. Rules that make sense, systems that behave, boundaries that stay out of reach. When we build simulations, we optimize them. We make only what's needed when it's needed. In a simulation as big as the universe, a similar trick would be necessary. You wouldn't simulate every atom of every planet in every galaxy all the time. You'd focus on the areas being observed, like how a video game loads only the level the player is walking through. Certain quantum effects, like particles behaving differently when observed, make people ask whether observation itself could be part of the code. If things are only real when measured, is that a sign of a system that chooses when to generate detail? Some physicists have even wondered if the laws of physics themselves might show signs of being coded. There are patterns in mathematics that are elegant but hard to explain naturally. Pi, the speed of light, Planck's constant. These numbers don't just work. They fit together in ways that seem purposeful. In a simulated world, the constants would be part of the software, the deep rules that tell the system how to behave. In a real simulation, no matter how advanced, there would be limits on how much detail could be managed. If reality was just a little blurry at extremely tiny scales, or behaved oddly under extreme conditions, that might be a sign of those limits. Some researchers think that tiny effects, like unexpected noise in particle measurements or small patterns in cosmic rays, might be hints of this hidden structure. But what would it mean if we really were inside a simulation? Would it change anything about how we live, what we believe, or what matters? For many people, it might not. Whether a tree is made of atoms or pixels, it still gives shade. Whether your life is coded or chemical, your feelings are still real to you. But for others, it raises the deepest kind of questions. Who built the simulation? Why? Is it running for research? For fun? People have wondered if the simulation might include messages. Maybe hidden patterns in nature are like comments in code, signatures left by the builders, or maybe the simulation was never meant to be found. Perhaps we're like characters in a story, unaware of the pages we live on. The simulation hypothesis also changes how we see time. In a simulated world, time could be managed differently. It could be paused, rewound, or even looped. We might not notice if the system were reset or changed. Everything would adjust to the new rules. The stars, the sky, even our memories might shift without us realizing. If the universe is a simulation, what lies beyond it? Is there a real universe that built ours? Are we nested inside simulations within simulations, each one a level deeper than the last? When you think about how far we've come with our own technology, it's not impossible to believe that others, somewhere out there, or somewhen, might have gone even further. Still, there's no proof we live in a simulation. No one has found the code. No one has broken through the walls. It remains a possibility, not a conclusion. But it's a possibility that makes us look at everything differently, and that cosmic horizon. It might not be just the end of what light has reached. It might be the edge of the render, the place where the simulation stops showing us more. Because for now, that's all we're allowed to see. If the universe is infinite, does that mean infinite copies of you? In our part of the universe, matter is arranged in a specific way. Galaxies are grouped together. On one planet, Earth, life appears. Over time, that life becomes complex. It builds tools, makes music, writes stories, launches rockets. That whole history, all the way down to the shape of your fingerprints or the color of your childhood bedroom wall, depends on how particles were arranged at the beginning. But there are only so many ways you can arrange particles in a given space. It's a huge number, but still a number. And when we deal with infinite space, even the biggest number becomes small in comparison. In infinite space, every possible arrangement of matter that can happen will happen. The same arrangements will repeat. Not just close copies, but exact ones. Eventually, a bubble of space would form that's just like our own. It would contain a galaxy like the Milky Way, a star like the Sun, a planet like Earth. And on that planet, a version of you. This version wouldn't know they're a copy. To them, they are the original, just like you. They would be living their life, wondering about the universe, asking the same questions. And even farther out, much farther, there would be another version. But maybe that one made one different choice. They turned left instead of right. They decided not to call someone back. A small detail changed. Their life went down a different path. And farther still, another version made another different choice. There would be a version of you that became a pilot, or a poet, or moved to a city you've never seen. If everything out there follows the same rules, and space never ends, then this kind of repetition isn't just likely, it's expected. Of course, these copies wouldn't be nearby. They wouldn't be hiding behind the moon, or orbiting a distant star. They would be incredibly far away, much farther than we could ever travel. To reach the closest exact copy of you, the distances involved are so huge they barely make sense in normal numbers. Some estimates say it could be around 10 to the power of 28 meters away. That's a 1 followed by 28 zeros, a number so big we don't even have a name for it. So even if these copies exist, we'd never meet them. We wouldn't even know they're there. But the idea that they're out there changes how we think about our place in the cosmos. If there are infinite versions of you, what does that say about identity? Are you still unique? Does your life still matter? Some people find comfort in the idea, knowing that somewhere, some version of you might be living the life you always dreamed of. Others find it disturbing, like being stuck in a cosmic hall of mirrors that never ends. This concept is sometimes linked to what's called the Level 1 multiverse, a term scientists use for the idea of an infinite universe with repeating regions. It's different from other kinds of multiverse theories that suggest entirely separate universes with different laws of physics. The Level 1 multiverse doesn't need new dimensions or portals. It just needs infinite space and the same physics. That's all it takes for repetition to happen. Even in a universe with repeating regions, most of space might still be empty. It's not like every few light years you'd find a perfect Earth. These repeating regions are spaced so far apart that for all practical purposes, we're alone. Each copy is isolated by distance and time, but from a mathematical point of view, they're still there, echoing us. We also have to be careful with how we define copy, because physics doesn't care about names or faces. It deals with how particles are arranged, how energy flows. If two systems have the same arrangement of particles, they're considered the same. So a copy of you doesn't need to have your memories stored in the same way. It just needs to have the same physical structure. If every neuron in your brain is arranged the same way and firing in the same pattern, then that copy would feel like you. From the inside, they would believe they are the original. Maybe this version of the universe isn't the first, or the center, or the most important. Maybe we're just one tile in a vast cosmic mosaic, no more real than any of the others. And if that's true, it raises the possibility that reality itself might not be as fixed as we think. In a universe of infinite variation, where everything that can happen will happen, it becomes harder to say what's normal or what's rare. Every moment, every choice, every version of reality exists somewhere. But could we ever prove this? Right now, the idea comes from theory, from math and logic. It's one of those cases where science pushes up against the edge of what we can test. And when that happens, science starts to sound like philosophy. Still, the idea is hard to ignore because it might be the natural conclusion of what we already know. Space is expanding. The observable universe is just a patch. The same rules of physics seem to apply everywhere we look, and if that pattern holds, then the copies are out there. Somewhere, right now, a version of you might be listening to this exact sentence, in a room just like yours, wondering the same thing you're wondering, and just like you, they're thinking, what if I'm not alone? Entropy and infinity. Can heat death happen in a universe without limits? In our everyday experience, things fall apart. Ice melts, fires burn out, batteries run down. This is the law of entropy at work. It says that over time, systems tend to move from order to disorder, from energy that can be used to energy that is spread out, thin and useless. It's why hot things cool down when left alone, why engines wear out, and why all living things eventually die. Entropy is one of the most solid rules in physics. And it's not just about small things, it applies to the universe as a whole. The idea of heat death comes from this. If everything moves toward disorder, then the universe itself must be doing the same. Over immense stretches of time, stars will burn through their fuel. Galaxies will go dark. Even black holes will slowly evaporate. What's left is a thin, cold mist of particles spread across space, with no structure, no light, and no energy differences to drive change. This state is sometimes called thermal equilibrium. Everything is the same temperature. Nothing interesting happens. But what happens if the universe is infinite? Can a universe without limits still run down? Or does the concept of entropy start to behave differently? To begin with, in a universe with infinite space, you can have an infinite amount of matter and energy. But entropy, as we understand it, still applies. It works locally. In patches of space, from star systems to galaxies, entropy keeps increasing. In a small room, heat spreads from a fire to the walls. On a cosmic scale, it spreads from stars to the empty void. The direction is always the same, toward evenness, toward the same temperature, the same energy level everywhere. If space is infinite, though, there's always more room for things to happen. You can imagine one part of the universe where stars have all burned out, and another part far away, where new stars are still being born. Each part has its own clock, running on its own timeline. In theory, there could always be places where entropy is still low, where order exists, even while other parts have already gone dark. But there's a catch. If entropy increases everywhere, even if slowly, then every region will eventually reach a high entropy state. The only way to avoid heat death is if there's something resetting the clock, some process that brings low entropy back again. On Earth, this happens in small ways. For example, plants take sunlight and build complex molecules. But that process still uses the energy flowing from the sun to space. It doesn't reverse entropy, it just borrows the local flow for a little while. Some scientists have wondered if the universe as a whole might contain these reset mechanisms. One idea is that black holes, as they evaporate, might seed new regions of space with low entropy conditions. Another idea is that quantum effects in empty space might allow tiny patches of order to appear out of the chaos. These patches could, in theory, grow into new universes, fresh starts where entropy is low again. This would mean that while our universe might grow cold and dark, new ones could sprout from its ruins, each starting the process over again. No one knows if they happen, and even if they do, each individual universe still faces its own version of heat death. The reset, if it exists, might not stop the process. It just moves it somewhere else. Now imagine an infinite universe, not just in space, but in time. That changes things even more. If time goes on forever, and entropy always increases, then doesn't that mean all energy will eventually be used up? It seems like it would. Even if there are infinite regions, each one with its own stars and galaxies, all of them would slowly move toward the same fate. Some thinkers have proposed that in an infinite universe, entropy might not be a one-way street. That, just by chance, order could appear again from disorder. If particles randomly move into the right places, even for a moment, a new structure could form. This is known as a fluctuation. But to get a fluctuation big enough to form a new universe, or even a single star, would take an immense amount of time, much longer than the current age of the universe. In fact, the numbers involved are so large they go beyond anything we usually deal with. It gets stranger. In an infinite universe, some physicists argue, the odds of small fluctuations are far higher than big ones. So if order does return, it might not be a whole galaxy or planet. It might be something small, a brain for instance, appearing briefly in the void with fake memories of a life it never lived. This odd idea is called the Boltzmann brain scenario. It's disturbing, but it shows how deeply entropy shapes our understanding of time, space, and even identity. The real mystery is whether entropy has a final limit. Is there a maximum entropy that the universe reaches, where nothing more can happen? Or is it always possible for the universe to become more disordered, more spread out, more even? If space and time are infinite, then maybe entropy is too. That would mean the universe never really ends. It just keeps changing, getting flatter, colder, and more quiet, forever. This is where the idea of heat death becomes a bit fuzzy. In our part of the universe, we can predict how stars will burn out and how galaxies will fade, but we can't yet see the whole picture. Maybe there are regions where new energy is still being created. Maybe there are cycles or structures in the fabric of space that slow down entropy or reverse it. Or maybe entropy is the deepest law of all, and nothing escapes its grip, not even in infinity. The challenge is that our tools and theories are built for what we can observe. We know how entropy works in labs, in engines, in living cells. We've modeled how it plays out in stars and galaxies, but beyond the observable universe, we don't have data, we have math and logic. But those things only go so far when we step into the unknown. Maybe heat death isn't a clean ending, but a fading process without a final point. Maybe it's more like a song that gets quieter and quieter until it's just a whisper in a field of silence. Or maybe it's like a tide, rising and falling across regions of space and time, bringing order and disorder in waves. Does the end of the universe imply the end of meaning? When people think about the end of the universe, the images that come to mind are cold, dark, and still. It's the kind of picture that feels final. If the universe ends in any form, does that change what anything means? If all things must vanish, does that include meaning itself? Telescopes and equations can describe what might happen to matter and energy, but they don't tell us how to feel about it. If everything that exists is moving towards stillness or collapse or fading into the void, what does that say about us, our lives, our choices, our awareness? People have asked about the meaning of life for as long as there have been people. But when you place that question against the scale of the universe, its age, its size, its possible ending, it starts to feel different. The universe doesn't seem to care. It just expands and shifts and moves according to laws we're still trying to understand. And in that silence, it's easy to wonder if meaning is something we've invented just to fill the space between stars. For some, the idea that everything must end makes life feel fragile, maybe even pointless. Why strive? Why love? Why build, if in the end it all disappears? A person might live a good life, but then they die. A civilization might rise, but then it crumbles. A planet might thrive, but then its star goes out. And even if we somehow found ways to stretch time, survive through machines or spread across galaxies, we would still be up against something bigger. Energy keeps dispersing. Entropy keeps growing. The end still comes. But for others, the same picture leads to a very different feeling. If everything is temporary, then every moment matters more, not less. Meaning isn't erased by an ending, it's created by what happens before it. A sunset is beautiful, not because it lasts forever, but because it doesn't. A song ends, but that doesn't stop it from moving you. A life might be brief compared to the life of a star, but that doesn't make it empty. It just makes it rare. Some philosophers have said that meaning is something humans bring into the world, not something we find waiting there. The universe may not speak to us, but we speak into it. We think, we create, we imagine, we suffer, we care. And in doing so, we make something real out of something silent. We are meaning makers. Still, the idea of an ending can cast a shadow, especially when we imagine endings on a cosmic scale. A heat death where everything is evenly spread, with no light and no change. A big rip where space itself is torn apart. A collapse back into a single point, erasing time. These endings are more than physical. They're emotional. They suggest a kind of silence deeper than death, a stillness that no thought can survive. So does that silence undo the value of what came before? Some would say no. Even if the universe forgets us, we were still here. Our thoughts, our struggles, our hopes, they were real. They mattered, even if only to us. And maybe that's enough. Maybe the meaning of life isn't about lasting forever. Maybe it's about being aware for a while in a universe that mostly isn't. Others push the question further. If the universe ends, does that mean everything ends? Could there be something beyond that we don't yet understand? Some greater structure or reality where what we do is still held, still remembered? That's not something we can prove, but it's a hope some people carry. Not just for themselves, but for everything that ever lived. Religions have often offered answers to these questions in many different ways. Some speak of souls, or of rebirth, or of eternal realms beyond space and time. Others focus on unity, or cycles, or purpose written into the world itself. These beliefs don't always agree with physics, but they come from the same human need, the need to know if what we are and what we feel matters in the long run. And yet physics itself sometimes opens the door to strange possibilities. Maybe new universes can form. Maybe time restarts in another place. Maybe information is never lost, only changed. Some theories suggest that what we call the end is just a transition, a kind of passing through a deeper layer of reality. If so, the story might still go on. But even if none of that is true, even if the universe simply ends and nothing follows, it doesn't erase the lives we live. It doesn't undo our stories, our friendships, our fears and joys. Those things happened. They mattered while they did. Meaning doesn't have to stretch forever to be real. Sometimes it's enough that it was ever here at all. And if meaning depends on awareness, then maybe the brief spark of life in the universe is exactly what gives it weight. The stars don't know they're shining. The planets don't know they're spinning. But we do. We look at the sky and wonder. We ask questions that have no easy answers. We care that we exist. That may be the rarest thing of all. Meaning can come from the ways we connect, the things we learn, the beauty we see, the kindness we give. That's a kind of answer that doesn't depend on what happens in 1 trillion years. It's something we can live by now. In a universe that may one day grow cold and quiet, the warmth of human meaning could be the most surprising thing of all. And on that inspiring note, today's journey comes to an end. If you enjoyed this voyage, leave a comment, leave a like, and consider subscribing to the channel. Thanks for watching.